Good afternoon, sir. We'll begin the session after 7 minutes.
Good. Yeah. So you are a research scholar there in IISER, Bhopal?
Yes, sir.
What are you working in?
So I'm working on dynamics of switch systems of differential, switch systems of differential equations.
Oh, I see. Okay. Yeah. I see. So it is not one-dimensional, is it?
No.
I see. You have a system of differential equations. And then when you say dynamical system, what do you study?
So basically the stability of such systems.
Limiting distribution and so on. Okay.
Yeah.
Not that you look at the map, x going to fx, f of x and so on, and then look at the invariant distribution and such things?
Not really, sir.
Not really. Okay. With whom are you working?
So Dr. Nikita Agarwal.
Oh, Nikita, I see. Okay, good.
Yeah.
Very good. Mm-hmm. Yeah. So you look at ODE or PDE?
So ODE. System of, yeah.
I see. System of linear, right?
Sorry?
Non-linear equations, right?
Yes.
Yeah. Okay. Mm-hmm. I see. And yeah. Is it in 2-3 dimensions or general n?
So right now I'm working in lower dimensions and we'll try to extend it later. Yeah.
Right. I see. Okay. Mm-hmm. So where did you do your master's?
So I'm an integrated PhD scholar, so I did an MS from here only.
Oh, I see. Good.
Yeah.
Okay. Yeah. Okay. So, if you are not busy with other any works, let me ask you. Okay, if you are busy, you can stop answering and then do your work. Okay. So, in your MSc, second year, what are the courses you had?
My internet is gone probably.
Yeah. I think he didn't hear your question.
Yeah.
I think he didn't hear your question.
Oh, I see. Okay.
Yeah, I'm sorry. Something happened to the internet. Yeah.
That's okay. So, no. By the way, what is your name?
So Swapnil.
Swapnil. Oh, Swapnil. Okay, great.
Yeah.
All right. So, now what are the topics you had in your MSc final year? Let us say papers. You tell me the papers.
It's been quite some time. So.
Okay, fine. Don't worry. So you had functional analysis?
Yeah.
And harmonic analysis?
No, it was optional. I didn't opt for it.
I see. And you had ODE, PDE?
Yes.
I see. And anything to do with physics?
Not really.
No, I see.
Yeah.
So in functional analysis, did you learn Hilbert space and Barak space and such things?
Yes.
And spectral representation theorem or not?
I did a reading course on that. So,
yeah.
Okay. Yes.
I see. Very good. Yeah. Do you stay in the campus there?
Yes, sir.
Okay.
Professor Rao, are you in Chennai?
Pardon me?
Are you in Chennai? This is Ravi from Mysore.
Yeah, Ravi.
Yeah.
Yes. So how are you?
Fine, thank you.
How is Vasudeva?
Vasudeva is fine. Yeah, it's fine.
Very good. And I forget the other name. There, somebody else in the department. Please tell me.
Professor Mohan and Hebbar.
Mohan and Hebbar. Mohan retired, right?
Yeah. Mohan retired long back, 2003.
And what about Hepar?
Hepar also retired 2009. Yeah.
Ah, Hepar also retired. I see. Mm-hmm. Okay, I see. And we have this other one, Andhra, right? Forgot his name.
Divanji.
Huh?
Divanji.
Yeah, Diwanji, correct. Diwanji.
He's there. He's there.
Oh, I see. Okay.
Yeah.
And only, oh, wait a minute. Then how many are in the department now? You and Diwanji are the only people, is it?
Oh, we were 3 and we continue to be 3. We were 3.
Uh-huh. But Vasudeva also retired, right?
Yeah, he retired long back. Yeah.
Okay, then who are the 3? You, Diwanji, and
Biradar.
I forgot. Yeah, correct. Brother.
Right. You remember.
Very good.
Okay, good afternoon, everyone. I am Swapnil and I'll be hosting today's afternoon session. I invite Professor B.V. Rao to continue his lecture on set theory. Over to you, sir.
Okay, thank you, Swapnil. Okay, so welcome to all of you. So last we were, okay. So first, let me explain what we have done so far. In the first episode of the serial, I have explained about axiom of choice and some equivalents of that. And I also explained why we are specializing in this axiom and not the other axioms. What is the specialty of this axiom? Then we discussed about ultrafilters, filters, and so on. And suddenly you land into very serious problems even with those. And in the second episode, we talked about, in the first episode, we already talked about 2 equivalents of axiom of choice, Velator's principle and John's lemma. And then in the second episode, we talked about well-ordered sets. Okay? And I said that the mental picture you should have of a well-ordered set is a people standing in a line. Okay? First person, second person, and so on. Okay? And then after showing that if you have 2 well-ordered sets, they are comparable in the following sense. Either they are order isomorphic or one of them is order isomorphic to an initial segment of the other. Okay? And of course, intuitively it is obvious. You imagine 2 queues of people. You make a correspondence between the first fellow in each queue, second fellow in each queue, third fellow in each queue. Go on doing like this. You build a ladder, so to speak. Somewhere you have to come to an end. Okay? At that time, you see what happened. So that is what we did. Then we were discussing about ordinal numbers. That is what we did. Okay? So that is where I start my story now. Okay? An ordinal number is a transitive set which is linearly ordered by the relation belonging to. And of course, it is a little abstract, so I have already given you examples. Empty set is an ordinal. The set consisting of empty set is an ordinal. This is denoted by 0. This is denoted by 1. This is denoted by 2. And of course, some of you who are not exposed to logic and set theory would think that why am I complicating life? I have the figure 0 here, I have the figure 1 here, I have the figure 2 here. Then why are you introducing these things? Okay. Sorry. This is a convenient way of defining these things, integers and so on. You see, these are the pictures that were taught to us right from beginning. And if you write in Hindi, these pictures will be different. If you write in Bengali, they will be different, and so on. But this will be same all over. And secondly, here there are several pictures, and here there is only one basic picture, empty set. Everything comes out of it. Okay. You know, you can philosophically say that the whole world is built up out of nothing. Okay. And in general, as you can see, if you have defined, you keep on defining. If alpha is an ordinal, then alpha union the singleton alpha is an ordinal. Okay. This we shall denote by alpha plus 1. So ordinals are unending. I quietly said that this is an ordinal, but of course, how do you know it is an ordinal? Well, if you take any two elements here, okay, one belongs to the other. Because if you took two elements from here, then because alpha is an ordinal, one belongs to the other. You can't take two elements from here. So if you take one element from here and one element from here, then this element belongs to this alpha. Therefore, that linearity holds, and it is transitive. By the way, what is transitive? If there is something in your set X, and if there is something else in this X, namely Y belongs to X, then Y should also be in your set. And here, if you take a thing from here, X, and a Y belonging to that X, then of course Y is here because this is already transitive. But if you take this as X, and if Y belongs to this, then of course Y is here. So this is the ordinals. And so this is the way we define ordinal. You should think of first, second, third, fourth, okay, order. And Haimanti talked about, and I also briefly talked about cardinals, okay, two sets of the same cardinality and so on. Those things you should think of as 1, 2, 3, 4. There is no order, just 1, 2, 3, and so on. Okay. This is first, second, third. Okay. And if alpha is an ordinal, there are many properties of the ordinals. Okay. And I would not like to bore the hell out of you with all the trivial properties. Everything can be proved just by using definitions. Okay. So I will read out some and explain some. Suppose you have an ordinal, and suppose beta is here. Then beta itself is an ordinal. Proof. Is beta transitive? Yes. If something is in beta X, and if Y belongs to that X, is that Y in beta? Yes. Okay. Because X belongs to beta, therefore X belongs to alpha. And Y belongs to X. Okay. Therefore, Y is also here. Okay. This is transitive. Alpha is an ordinal, by the way. Okay. And beta is in alpha. You see, many of these things are absolutely trivial because every ordinal consists of the preceding ordinals along with the entire set you have so far. Okay. So that is why. Okay. And any two things in beta are comparable. Now, where are we heading? Let me tell you. Well, we are heading to several properties, but more important, every well-ordered set is isomorphic to an ordinal. That is where we are heading. Okay. Therefore, just like equivalence between sets, equivalence between two well-ordered sets can be defined. I have already done this. Last time we discussed two well-ordered sets being ordered isomorphic. Now I am going to show every well-ordered set is isomorphic to one of these ordinals that we have described. So you can take them as a standard thing. Okay. If alpha is not equal to beta, they are ordinals, and alpha is contained in beta, then alpha must belong to beta. Okay. Why? Alpha is a subset of beta, but alpha is not equal to beta. Therefore, there are elements of beta which are not in alpha. So take the least element, gamma. Okay? That should be equal to alpha. Why is that so? Because when you took the least element gamma, okay, what does it consist of? Any ordinal consists of all the previous things. Okay? So gamma consists of all the previous things. But all the previous things is alpha. Why? Because gamma is the least thing which is not in alpha. So, therefore, that is why. Okay, I think when it comes to trivial statements, the more you explain a trivial statement, it appears non-trivial. Okay? So I will reduce my explanation. If you take two ordinals, alpha and beta, one of them is contained in the other. Okay? Ordinals are comparable. Okay? Do not confuse. Ordinal itself is a transitive set. If there are two things, x and y, in the ordinal, either x belongs to y or y belongs to x. That is a different matter. Now I am saying if you take two ordinals, one of them is contained in the other. Of course, why? Take the intersection, gamma. Then gamma is also an ordinal. Okay? It is transitive and so on. Okay? And if gamma is neither alpha nor beta, then gamma is an ordinal which is contained in alpha because of this equation. It is not equal to alpha. Therefore, gamma belongs to alpha. Similarly, because of this equation, gamma is contained in beta and gamma is not equal to beta, if you tell me. Then gamma belongs to beta. Therefore, gamma belongs to alpha, gamma belongs to beta. Therefore, gamma belongs to alpha intersection beta. That means gamma belongs to gamma. Okay? Which is not possible. A set cannot belong to itself. Remember, we have regularity. Okay? Which prevents that possibility. Okay. Now, we shall denote by on the class of ordinals. As you can see, ordinals do not form a set because given any ordinal alpha, there is something which strictly includes it. Namely, the ordinal alpha you have given me, union, the set consisting of that ordinal. Okay, this you have already seen here. Therefore, the collection of ordinals is not a set, but it is a class. Don't worry. Of course, you can consider initial segments of this class and talk about it. You know, sometimes you feel very uncomfortable. If on is not a set, why are you talking about it? Okay, okay, if you don't like it. Whatever statement I make about on, you take a subset and then look at the same statement. That's all. Okay.
Sir,
yeah.
I couldn't understand why you said that an ordinal is not a set. I think.
The collection of ordinals.
Yeah. Yeah.
Because collection of ordinals, this is unending. Okay.
Yes.
Yes.
Then why is not it a set? I mean.
What?
I mean, you said na that on. Perhaps you said that on is not a set.
Yeah, on is not a set. Yeah, that is what I said.
But why? Why? I mean, what is class and why?
Okay. You see, class is simply the collection of all sets satisfying a certain condition. Okay, if you have a formula, phi x of one variable, then the set of all, the collection of all sets x satisfying this formula is called a class. And a class may be a set, may not be a set. So at this stage, you don't have to really worry. If this is bothering you, okay, then you don't have to worry. All right. I am not going to.
Hello, sir.
Yeah.
So how do you prove this is a class?
How? Oh, because I can write a statement phi x. phi x is the following statement. Okay.
No, sorry, sir. My question, I got it wrong. My question was, how do you prove this is not a set?
Oh, how do I prove that this is not a set?
Yeah.
Very good question. Okay, so let me think about it. Okay. Yeah, you see.
Hello, sir.
Yeah.
Sir, I think you should show that this cannot be contained in any class, right? Something like that, right? This cannot be an element of any class.
Yeah, you see the whole
But
point.
how do you show it?
Okay, fine. I can show that. Let me explain. There is a way to describe all sets. Okay, and we shall go through it a little bit next time. That is why I am hesitating. Okay, so let me tell you briefly the story. Look at empty set. Okay, look at all subsets of that. Okay, empty set you denote by V0. The collection of subsets of that by V1. The collection of subsets of V1 by V2. In general, you can define V alpha as the following thing. Okay, I have to come to still certain things later on, limit ordinals and so on. Okay, if alpha is a limit ordinal, V alpha consists of all the previous things. If alpha is a successor ordinal, it consists of the power set of the preceding thing. So I keep on defining a collection of sets V alpha. Okay, now here is a theorem. Every set belongs to some V alpha. That's it. Okay, and you show that on is not a set by using that theorem. Okay, every set.
Hello, sir. You said every set belongs to one of the V alphas, right?
No, every set belongs to one of the V alphas. That's the theorem.
And V alpha you get by taking power sets successively.
Correct, exactly. Okay, we will discuss that again.
Okay,
slowly.
sir.
Okay, sure. So, in other words, you can describe all the sets. Okay, there is nothing more. Okay, I shall explain that a little later, maybe. I don't know either today or tomorrow. Okay.
Sir, this is Suresh here.
Yeah.
Sir, one can also use the fact that the union of any set of ordinals is an ordinal which is greater than all the ordinals in the set.
Yeah,
if
true.
you assume this fact, then you cannot say that on is a set, because if it were a set of ordinals, there would be a larger ordinal, which is a contradiction.
Okay, good. That's another way of looking at it.
Hello, sir.
It is.
Sir, but that is not necessary, right? I mean, if it's a set, it necessary. I mean, it need not contain a largest element, right?
No.
No, that is not what I'm saying. I'm saying you take any set of ordinals, take their union, that is an ordinal which is greater than all the ordinals in the set. That is all I'm saying.
Oh, okay.
Yeah. That's a simpler argument than what I was thinking. Okay. If you,
excuse me, sir.
Okay. If you
Excuse me, sir.
think that on is a set, then as Professor Fide said, look at the union. Union axiom allows you to take the union. Okay. And then add to this that set. That will be an ordinal. That's a very good argument. Okay. So that is much simpler than what I was thinking. Okay.
Hello, sir.
Yeah.
Sir, somebody was trying to say something.
Yeah, please say.
Sorry, sir. I wanted to ask a question on this subject because it was going on right now regarding the subject of classes. So you, when you said that class is it's a collection of sets which satisfy a certain formula given by certain formula phi of x.
Right.
This phi of x, this can't be arbitrary, right? So is it governed by certain rules, as in the structure of this formula?
Not necessary. You take any formula phi x of ZF, Gerbelow-Frankel set theory.
Okay.
And that's it. Okay? Yeah.
Okay. Yes.
But you see, somebody yesterday was saying that he will talk about Gödel-Bernoulli set theory and so on. That is different. Okay? They will talk about classes also. Okay, and so on. So you have to be very careful. When I said class right now, it is class in ZF. Okay? But there are other set theories like Gödel-Bernoulli and so on. Okay? Kelly set theory and so on. Maybe somebody will present something tomorrow. We will see that. Okay? But we will not enter into classes right now. So you don't have to worry.
Sure.
Yeah. Okay? Yeah, thanks, Suresh. Yeah. And then this less than is a linear order on ordinals. Okay? Because if alpha, beta are ordinals, then either alpha is contained in beta or beta is contained in alpha. And I defined alpha less than beta if alpha belongs to beta. Okay? Therefore, it is a linear order. And as I said already once, every ordinal consists of all the preceding ordinals. Okay? And if S is any non-empty set of ordinals, then the intersection is an ordinal. It is in your set S and it equals the least element of S. Okay? And why is that so? Take any non-empty set of ordinals, look at the intersection. To show that the intersection is an ordinal, okay, you have to show that two things. You see, it's all mechanical. There is nothing to think. Epsilon is a linear order. I should not say epsilon. Belongs to is a linear order. And it is transitive. But intersection of transitive sets is transitive. And intersection of linearly ordered subsets, you see, is again linearly ordered. Nothing to worry. So this is an ordinal. And this is the least element of S. Okay? And then, if S is any non-empty set of ordinals, union S is also an ordinal. But of course, earlier I said, okay, that this is already in S, but now I cannot say that union is again in S. And this is not any enigma. You can look at 0, 1, 2, 3, 4, 5, 6, take their union. Their union is omega, okay, or the set of all 0, 1, 2, 3, etc. That doesn't belong to your set S. S consists of only 0, 1, 2, 3, 4, etc. But not omega. Okay. And alpha union singleton alpha is the infimum of all beta, beta bigger than alpha. This is the ordinal next to alpha. That is why we have named it as alpha plus 1. Okay.
Sir?
Yeah.
So just a thing, I just thought that like let's say I'm taking 0 and 1. If I'm taking its union, then won't that be equal to 1? I mean, phi.
Yeah. Of course, it will be equal to 1. Definitely. Of any two ordinals, one is contained in the other. Definitely.
Yeah. So won't the union be an ordinal? And ordinal is a set.
If you took 0 and 1, their union is 1. Fantastic. That is an ordinal. If you took 0, 1, 2, their union is 2. That's an Agreed?
Yeah.
But suppose you take 0, 1, 2, 3, 4, 5, 6, etc. Then what?
Then the highest number, whatever we end in.
But that is not, there is not ending. It is unending.
Oh, okay, you are considering the whole sequence.
Only integers. Okay? I take only the positive integers as you are familiar with. I am not taking the class of all ordinals. Okay?
Okay.
I am only taking the first infinite limit here. 0, 1, 2, etc. Their union is an ordinal, but that is neither 0, nor 1, nor 2, nor 3, etc. That is the smallest ordinal, bigger than all these.
Yeah.
Okay? That's it. That's it. Very good. Very good.
Then why did you say that it's not a set? You said that it's not a set.
No. It is a set. It need not be in your S. You see? Okay, that's all. Is it okay? Or is there any confusion?
No.
If you take any set of ordinals, their union is also an ordinal, but that ordinal need not be in your set.
When you mean to say that if I'm taking 0 and 1, that would be 1, that need not be 0. If I'm
Wait. Be careful.
Yeah.
When you use the word need not, it means sometimes it may, sometimes it may. right?
Yeah.
Therefore, in this case, when you took 0, 1, their union is 1, which is in your set. Okay?
Okay.
If you take 0, 1, 2, in this case, the union is 2, which is in your set.
Yes.
Okay? But however, if you take 0, 1, 2, 3, 4, 5, 6, so on, only up to the first infinite repeat, then their union is the set consisting of 0, 1, 2, 3, 4, 5, 6, the infinite set, which is not 0, not 1, not 2, it is not in your set. Is it okay?
It is not finite. That's what you mean, maybe.
No, it is not in your set, that's all. Okay?
I mean, I'm not getting what you mean by it's not in my set. Yeah.
Okay. First of all, what is your set? Let us see. You are not getting this one. So first of all, what is your set?
My set consists of the phi's and it's, I mean, what to say?
Tell me.
Like alpha union set of alpha.
Sorry, not union set of alpha. Your set consists of the following things: 0, 1, 2, 3, 4, and so on. That is the set.
Yes.
Is it okay? You agree?
Yes.
Okay. So that is the set S.
That is the set S. Yes.
Okay. Take the union. Okay.
Union of 1, 2, 3. I mean 0, 1, 2, 3. All of them.
0 is a set, empty set.
Haha.
1 is a set consisting of empty set, right?
Yeah.
2 is a set consisting of empty set and set consisting of whatever. Okay. 3 is a set, 4 is a set, right? These are all sets. Okay. So take 0, 1, 2, 3, 4. This is my set S. Okay.
Yes, sir.
Agreed?
Yes,
This
sir.
set has 0 is a set in S, 1 is a set in S, 2 is a set in S. I take the union of all these sets which are in S. Okay?
Yes.
You understand? I take the union of all these things which are in S.
I take the union that translates to I take the union of 0, 1, 2, 3, which are all in S, right?
So that
That's
means that is this set consisting of 0, 1, 2, 3, 4, 5, 6, everything, right?
Everything. Yeah.
Very good. Is it in your set S? Does it belong to your set S? Again, I don't have to answer. You answer. What is your set? Remember, your set consists of 0.
Union of all the sets.
Wait. Again. Your set consists of, let us go from the beginning. I know where the confusion is coming. Okay? Your set consists of 0. 0 is an element in your set. 1 is an element in your set. 2 is an element in your set. 3 is an element in your set. Agreed?
Yes, sir. Yes.
These are all elements in your set. There is nothing else in your set. Agreed?
Yes.
Nothing. Okay. Nothing else in your set. Very good. Now you take the union of all these things. Okay. What does it consist?
Union of what? These things? I mean, union of. You said one minute.
Wait.
Yeah.
Okay. 0 is a set, right? Empty set.
Yes.
1 is a set, right?
Yes.
0 is a set. 1 is a set. 2 is a set. Agreed?
Yes.
Now, you looked at, you see, that is what I said. Many times I use the words collection, family, etc. so on. Okay? And here, because I am using the word set, okay, you probably have confusion. So let us look at the following set, which we shall now call family, because you are getting confused. Okay?
Okay.
Family consists of 0, 1, 2, 3, 4, etc.
It is not a set. It has some different name.
I just gave it a name. It is a set, right?
What is a set?
Yeah, because you are getting confused, I gave it a name, family. Okay? And this I will denote by S. Is it okay? What is in S? 0 belongs to S. Agreed?
0. Yes.
What is 1 belongs to S. Agreed?
Yes.
2 belongs to S. Agreed?
Yes.
Oh. Nothing else belongs to S, right? 3 belongs to S, 4 belongs to S, nothing belongs to S, right?
Nothing means 0.
Nothing else. Okay? So S is a set whose elements are 0, 1, 2, 3, 4, etc.
Yes.
Agreed?
Yes.
Oh. Nothing else. Okay. Now, keep it on your right side. Okay, keep it on your right side.
Yes.
Okay, that is a set S. Okay,
Yes. Yes.
you can call it family, you can call it set S. Okay,
Yes.
now look at your left side. Okay,
Yes. Huh.
0 is a set. Agreed?
Yes.
Empty set.
Yes.
1 is a set. You agree? This set.
Huh. Ha ha ha. Ha.
2 is a set. You agree?
Hmm.
So on the left side, you have certain sets, right? These are
Okay.
all sets which are elements of your right side thing, right?
Yes.
Okay. So take the union of all these sets on your left side. Okay?
Yes. Yes. I mean, does that not become a set?
Wait, that is a set.
Yes.
Okay?
Huh.
Does that set belong to the thing on your right side? Does that belong to the thing on the right side? Keep two sides separate. Don't confuse right now. Okay?
Ha 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 ha.
Okay.
Ha.
On your right side, there is a set S,
Yes.
which consists of 0, 1, 2, 3, 4, etc.
Yes.
Okay.
Yes. Yes.
Agreed?
Hmm.
On your left side, there is a set 0. There is a set 1. There is a set 2. Okay? On your other left side. Take the union of all these things. If you take the union of all these things, you will get S. Right? S doesn't belong to S. Correct?
So what doesn't belong to S?
S does not belong to S.
S does not belong to.
Agreed?
No. Why not? I mean, why does it not belong to S?
Okay.
Why S does not belong to S?
Why S does not belong to S? Okay. Now, again, go back to our question. That is why I said you keep two things on both sides. On your right side, you are keeping the set S, which consists of the points 0, 1, 2, 3, etc. Okay?
Yes.
So,
Yes.
what belongs to S? 0 belongs to S.
Yeah.
What belongs to S? 1 belongs to S. Okay? 2 belongs to S. Okay? 3 belongs to S. These things belong to S. Right? Nothing
Subsets.
else,
Oh,
right?
no. Huh?
Okay? Nothing else belongs to S. 0 belongs to S. 1 belongs to S. 2 belongs to S. 3 belongs to S, and so on. Agreed? If you take the set consisting of 0, 1, 2, 3, everything, does that belong to S? Does that belong to S? No.
I mean,
Wait. What's your confusion? Tell me. First of all,
sir, you said na that let's say I have a set as, I mean, any set as, or let's say this let's name the set as X to, I mean, in order to keep things separate. So X does not belong to X. That's what you say. You are saying?
No, yeah.
Okay.
No, X does not belong to X. Okay.
Okay. Oh, okay.
Okay.
I mean, X, I confuse between X is a subset of X and X belongs to X.
Okay, now that's fine. Agree.
Yeah.
You agree now?
Yeah.
Belongs to. It doesn't belong to you. Okay.
Oh, thanks.
Oh, great. Okay. Now, okay. So I will go back. This is where I said I am heading. Every well-ordered set is isomorphic to a unique ordinal. When I say isomorphic, it is order isomorphic. Okay? So, take a well-ordered set. I am going to imitate the same proof as I used when I proved that among two well-ordered sets, either they are isomorphic or one is isomorphic to an initial segment of the other. I use exactly the same thing. Now, why is this interesting? Because among every well-ordered sets, we have in some sense selected a representative, so to speak. Okay? If you take two ordinals, they are not order isomorphic. Why? Because if you take two ordinals, alpha and beta, either alpha is less than beta, or beta is less than alpha, or alpha equal to beta, right? Therefore, if you tell me alpha is not equal to beta, then alpha is either less than beta or beta is less than alpha. In any case, one of them is an initial segment of the other. And last time we saw a well-ordered set cannot be isomorphic to an initial segment. Therefore, for two different ordinals, okay, they are not isomorphic. What this says is the following: every well-ordered set is isomorphic to a unique ordinal. Okay? So that is the importance of this one. Okay. Now proof, I will not go in complete detail, but I will explain. The idea is exactly same as last time, as I said. Suppose W be a well-ordered set. If W is empty, it is an ordinal. Done. It is 0. Assume W is not empty. Okay? Now, I want you to keep the following picture in mind. I have ordinals 0, 1, 2, 3, 4, etc. And then at the end, I have got infinity, which I denoted by omega, then omega plus 1, etc. so on. It goes on. Okay, on the right side. On the left side, I have your well-ordered set. Okay? And as I keep on telling, imagine your well-ordered set as people standing in a line. Okay, there is a least element. And then after that, next least element and so on. Okay, people standing in a line. So build a ladder. That is what I am going to do. Okay. Unfortunately, you see, for all these mathematical proofs, number one, you should see the idea. Number two, the execution of the idea without using words like etc., dot, 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 so on and so forth. You know, these are the words. When I say etc., you may say, no, I don't understand what is that etc. When I say dot, 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 you can say, I don't understand what is there in the dot. If I say continue like this, you can always say, no, no, sorry, how do I know I can continue? You see? So there are lots of problems. That is why execution of the proof, okay, looks a little formal, looks a little abstract, and so on, simply because we go a little away from intuition. But this is just the intuition made precise, no more, no less. Okay. So I have my well-ordered set on the left side, okay? And on the right side, I have ordinals. Okay. I define fx is equal to alpha if the initial segment wx is isomorphic to alpha. Okay. To tell you the analogy, last time I have defined fx is equal to y if the initial segments at x and y are isomorphic, okay, and so on. Okay. But anyway, let me not go back to that. That might create more confusion. So carefully look at that. Left side is my well-ordered set. I define for x in the well-ordered set fx to be equal to the alpha if the initial segment wx, all things below x, is isomorphic to the ordinal alpha. For example, if fx is alpha, then the isomorphism between wx and alpha is uniquely determined. Okay? This only says fx is equal to alpha if these are isomorphic. And you see the beauty with well-ordered sets that we have discovered last time. Okay? Any order isomorphism between two well-ordered sets is unique. There is no choice. Okay? If you have groups, if you have vector spaces, etc., isomorphisms may be many, but not for well-ordered sets. Order isomorphism is only one. Okay. Therefore, there is only one isomorphism, if at all there is. If fx is equal to alpha and fx is equal to beta, alpha not equal to beta cannot happen. That means for every x, if at all there is an alpha, there is only one alpha. You cannot have fx equal to alpha and fx equal to beta. Why? Because then wx is isomorphic to alpha, wx is isomorphic to beta. In particular, that implies alpha and beta are isomorphic. Okay? But that cannot happen. If alpha is not equal to beta, either alpha belongs to beta or beta belongs to alpha. So if you tell me alpha, beta are isomorphic, the well-ordered set is isomorphic to an initial segment. So no way. Similarly, if f of x is equal to alpha and f of y is equal to alpha, x not equal to y cannot happen. Therefore, two different points cannot go to the same alpha. Okay. Of course, if anything goes to anything else at all is a different matter, we will see. Okay. If fx is equal to, so for every x, if at all there is an alpha, that alpha corresponds to only one x. Again, proof is trivial. If you tell me fx is alpha, fy is alpha, both are alpha, and x not equal to y, okay, they are different, then wx is isomorphic to alpha, wy is isomorphic to alpha. Okay. Therefore, wx is isomorphic to wy. But you told me x is not equal to y. Therefore, x less than y or y less than x. Therefore, well-ordered set is isomorphic to an initial segment. No way. Okay. So, for every x, there is at most one alpha. For an alpha, there is at most one x. Okay. But is there any x at all for which fx is defined? Yes. If alpha is the first element of W, then WA is empty set, A is the first element. So WA, the initial segment is empty set, but this is 0. Okay. So this is f of A is 0. Agreed? 0 is the empty set. WA is also empty set. They are all isomorphic. That is why we allow empty set also. Okay. Generally, it doesn't make sense to talk about empty well-ordered set. But as I said last time also, if you are uncomfortable with this empty set business nonsense, you can go to the second element and so on. Anyway, if f is defined for x less than y, okay. Now look again, please remember, on your left side are W, points of W standing in a line. If for a point x in W, fx is alpha, then for all y below x, okay, also it is defined. That is what I am going to tell you now. If f is defined for x less than y, and fx is alpha, fy is beta, then alpha is less than beta, and the isomorphism between wy and beta is extension of the isomorphism from wx to alpha. What the hell does this mean? In your left-hand line of points in W, take a point x in that line and take a point y above x. Suppose fx is alpha, fy is beta. Then, first of all, I am saying alpha is less than beta. And secondly, the isomorphism between the initial segment wy and beta is extension of the isomorphism from wx to alpha. And that is essentially uniqueness of other isomorphisms, okay? So I don't want to explain more. For each x, there is an alpha such that fx is alpha. Why? This is easy. From what I have said, f is defined on an initial segment of W. Because remember, just now I said, if it is defined for y, it is defined for all things below. Therefore, f is defined on an initial segment of W. If the complement is not empty, take its first element and you can extend it in the obvious way. Remember, ordinals are unending. Okay. Therefore, there is a isomorphism from either W into ordinals, in which case it is done, or from an initial segment, in which case if it is an initial segment, you can extend it. Therefore, this is defined. Okay. So I just leave it at this, so you can think about it. So basic upshot is the following: every well-ordered set is isomorphic to an ordinal number. Okay, ordinal numbers beta of the form alpha plus 1 are called successor ordinals, and those which are not successors are called limit ordinals. For example, omega is a limit ordinal. Okay. And omega plus omega is a, look at here. When I started ordinals or well-ordered set even before ordinals, I gave these examples of ordinals. 0, 1, 2, but I changed them 0, 1, 2, omega. This is a limit ordinal. And 0, 1, 2, omega, omega plus 1, omega plus 2, etc., omega plus 3, omega plus 4, etc., and put omega plus omega. This is also limit ordinal. Okay? So these are not limit ordinals. So anything which has a previous thing is called a successor ordinal. Other things are called limit ordinals. Okay. And now we shall more or less stop our discussion about ordinals so far. I just mentioned one more thing. Many times I talked about alpha plus 1, all these things. So it will be an enigma for you. What the hell is the plus symbol? Is it really plus? Does plus have any meaning? Yes. One can develop ordinal arithmetic, but we shall not. What is the idea of developing ordinal arithmetic? Given two ordinals alpha and beta, you first get disjoint sets A and B such that A is isomorphic to alpha, B is isomorphic to beta. Okay. You might ask, how do I get? Very simple. You take this 1, I belonging to alpha. This set of all pairs, first coordinate is always 1, second coordinate is I. Okay. This is order isomorphic to alpha. You map 1, I to I. Similarly, B is 2, I belonging to beta. These are disjoint sets. Every point here has first coordinate 1. Every point here has first coordinate 2. They are disjoint sets. They are well ordered. Okay. Now, you look at the set A union B. Because they are disjoint, you don't have to worry. I define an order on A union B. How? First, usual order on A. Okay. Of course, you might wonder what the hell is usual order. For every point in A, first coordinate is 1. Therefore, don't worry. The order depends only on the second coordinate. Similarly, for every point in B, the order depends only on the second coordinate. What about for points between A and B? All points of B appear after all points of A. Okay? So if there are two lines, okay, you look at the first line, after it ends, you continue the second line. Okay? That is it. And this is a well-ordered set. It is isomorphic to a unique ordinal from what we have proved. That is called alpha plus beta, that ordinal. Okay? Therefore, you can define sum of two ordinals, alpha plus beta. And there are many interesting things that happen here. For example, you can talk about 2 plus omega, okay, or omega plus 2. They are different. When you say 2 plus omega, you will put a set consisting of 2 points, and then you will put this set omega, 0, 1, 2, etc. so on. Okay. So 2 plus omega consists of 2 points, and then these infinitely many points. But as far as order is concerned, that is same as omega. You see, first point, second point, third point, fourth point, nothing. And omega plus 2 is different. Why? What is omega? Omega is this set. Okay, 0, 1, 2, etc. This whole thing is omega. Okay, plus 2. Add 2 more at the end. It is this one. Omega, omega plus 1. Okay, up to this. So, omega plus 2 is this well-ordered set. 0, 1, 2, omega, omega plus 1. Okay. Therefore, commutativity of addition fails. Similarly, you can define product of two ordinals, alpha into beta. Okay. But I shall not discuss product of ordinals and so on. You can develop arithmetic, and there are beautiful theorems, factorizations and so on. Okay, so that is the story about ordinal numbers. Now, as you can see, now let us try to tie up with what you have learned in the last 2 lectures from Professor Sarvadhikari. You talked about cardinals. So look at this one. Okay. This is a well-ordered set. As a set, this is countable. Okay. This is countable. Why? Because you can map this to 0, this to 1, this to 2, and this to 3, 4, 5, 6, 7, 8, and so on. Okay. So this is a countable set. This is also countable. Okay. Why? Because you can map this to 0, this to, okay, 5, okay, this to 2, this to 4, this to 6, and etc. so on, and this to 1, this to 3, this to 5, and so on. Okay. Oh, one more is left over. So, okay, all right. Doesn't matter. Okay. So, this is a countable set. This is also a countable set. However, please remember, this ordinal is different from this ordinal. Why? There is no isomorphism between these two things. You see? You can quickly see that. Okay? Many times it is difficult, but here the sets are standing before you. If at all there is an isomorphism, 0 must go to 0, 1 must go to 1, 2 must go to 2, omega goes to omega, omega plus 1 to here, and so on. That's all. These are the. Okay. So they have the same cardinality, but they are different well-ordered sets, as well-ordered sets. And now I shall specify cardinal numbers among ordinals. Okay. Alephs are cardinalities of well-ordered sets. Okay. You take a well-ordered set, its cardinality is called an aleph. I shall be a little more precise in a minute. X and Y have the same cardinality if they are in 1-1 correspondence. Okay, you remember it from yesterday. Therefore, you should be careful now. 1-1 correspondence is different from isomorphism. Isomorphism, order preserving map. 1-1 onto order preserving. So, but if you take a well-ordered set, there is a smallest alpha such that cardinality of the well-ordered set is same as the cardinality of alpha. Why? Because if you take any well-ordered set, I said, first of all, there is some beta such that W is order isomorphic to beta. Okay? That is what we have proved earlier. Every well-ordered set is isomorphic to a unique ordinal. Okay? Therefore, every well-ordered set is isomorphic to beta. In particular, it is in 1-1 correspondence with beta. Okay? Order isomorphism is a 1-1 correspondence more than that. Therefore, W and beta have the same cardinality. Thus, ordinals up to and including beta, which are in 1-1 correspondence with W, is a set. Okay? Look at all ordinals up to and including beta, so that W is in correspondence with that. Then, take that set, take the minimum. Okay? Every subset of ordinals has a minimum because this is well ordered. Okay? And again, if you are getting doubt why it is well ordered, because by definition of ordinal, it is linearly ordered. And if it is linearly ordered, why is it well ordered? Because of regularity. Okay? Given any set, there is a smallest element under belonging to order in that set. Okay. Let us denote it by theta. Okay. So there is a smallest ordinal theta such that as a set, W is in 1-1 correspondence with theta. Okay. There is no alpha less than theta such that alpha is in 1-1 correspondence with theta. Okay. Theta is the smallest. In particular, what to conclude is the following. There are ordinals such that no ordinal below that is in correspondence with theta. Okay. And such things are called initial ordinals. Okay. There is nothing initial about it. They initiate a new cardinality, that's all. Okay. For example, if you look at 0 is an initial ordinal. Oops, sorry. Yeah. 0 is an initial ordinal, 1 is an initial ordinal, 2 is an initial ordinal. Okay. Because this is not in 1-1 correspondence with anything previous. This is an initial ordinal, but this is not an initial ordinal. Why? Because this set up to this has the same cardinality as this. This is also not an initial ordinal because this set is in 1-1 correspondence with this. Similarly, none of these are initial ordinals. Okay? But remember, omega is initial ordinal. You can write omega plus omega plus 1, omega plus omega plus 2, and so on, omega plus omega plus omega. Even that is not an initial ordinal. Okay?
Sir?
Yep.
How is omega, I mean, how does omega plus 2 have some correspondence with omega?
Okay.
You said.
This, I want to have this as the same correspondence with omega, right?
Yeah, you said.
Okay, I have written omega plus 3 here, but let us see. Okay. I make this correspond to 0. I make this correspond to 1. I make this correspond to 2. Okay. I make this 4.
You are comparing those two, I mean, the top set and the bottom set.
No, these two sets. Okay. You see, you said why this is not. This is in correspondence with omega. Is that right or not? What is your question?
Yes, you said that it has correspondence with.
This is in correspondence with omega. What does omega consist of? 0, 1, 2, 3, 4, 5, etc. Right?
Yes, sir.
Therefore, I have to make a 1-1 correspondence between this and this set 0, 1, 2, 3, 4, 5, 6, etc. Correct?
Yes, sir.
Yeah?
Yeah, yes.
I have to make, okay. This is the correspondence. This goes to 0. This goes to 1. This goes to 2. This goes to 3. This goes to 4. This goes to 5. This goes to 6, and so on.
Okay, sir.
Okay?
Yeah.
Okay, let me repeat. This goes to 0. This goes to 1. This goes to 2.
Okay.
This goes to 3. This goes to 4. This goes to 5. This goes to 6, and so on. All the elements here are made to correspond to 0, 1, 2, 3, 4, 5, 6, 7.
Yes.
1, 1 on 2. Agree?
I mean, it ends with omega. You mean?
What ends with omega? Nothing ends with omega. You see? You asked me to show the correspondence between this and omega, right?
Yeah.
What is omega? Omega is the following set: 0, 1, 2, 3, 4, 5, 6, etc. Dot dot dot. Is it okay?
Does the dot end somewhere?
No, it doesn't end with omega. Omega is this set.
Dot means it continues.
Continues forever, unending.
Oh. Okay. Then it's fine.
That's omega.
Then it's fine.
No, even if it ends with omega, no problem. Don't worry. Okay, you want me to make it correspond with that? I can also do that. But anyway, let me not. Okay. So, is it all right, or do you still have any doubt?
Sir, if it is finite, then I have doubt. How is it 1, 1 on 2? Infinite is okay.
Okay, ask the question again.
Yeah, so if the sequence ends somewhere, if it is finite, then I have problems. But
don't say if it is finite. Don't say it. What is it? You tell me.
the set 0, 1, 2, 3, ... omega, omega plus 1, omega plus 2.
Correct.
Right.
Yeah. Okay.
Right? This thing.
Yeah. Yeah.
So if this sequence ends somewhere, if this sequence ends somewhere, then I have a problem in corresponding it to like omega.
Why?
1 corresponding.
Wait a minute. Wait. Don't worry about looking at ending, unending. Do you agree this is a countable set up to here?
Yes.
Do you agree
Yes.
that it is a countable set? Omega, omega plus 1, omega plus 2.
Yeah.
Okay. Do you agree that union of two countable sets is countable?
Yes.
This is one more extra point. Do you agree if you add one more point to a countable set, it is countable?
Yeah.
Therefore, do you agree this is countable?
No. Yeah.
Therefore, this is in correspondence with 0, 1, 2, etc. so on. Up to here.
I mean, are you saying that they have the same cardinality or anything?
That is why I said be careful. When I said correspondence, it is 1, 1 onto map. When I say after isomorphism, it is different. Okay. 1, 1 correspondence. Okay. So they have the same cardinality. You are absolutely right. I am saying that they have the same cardinality. Is it okay? But that is the definition you learned yesterday, isn't it? Two sets have the same cardinality if there is a 1, 1 correspondence between them, right?
Yeah.
That's it.
Okay.
Okay. So.
Excuse me, sir.
Yeah.
Sir, if we consider this set omega, omega plus omega, and omega plus omega plus omega, and then such finite sums of omegas as defined here.
Okay.
So, like as we have shown this, the union of all these, I mean, yes, the union of all these ordinals, this would also be an ordinal.
So,
how would we denote this ordinal, sir?
We do not display omega plus omega plus omega plus omega, etc. Omega
that's the
into
notation.
Omega. It is called omega into omega. Okay?
Oh.
Sure.
Okay, sir.
And then you can talk about omega into omega plus 1, omega into omega plus 2. And then you can talk about omega into omega plus omega. Okay?
Okay, sir. So there is like there is a notion of polynomial expressions.
Of course there are. I said that there is unique factorizations and such things are also possible here. Okay?
Okay.
So there are, in fact, I think Calcutta had already done that. Okay?
Okay.
But we are not entering into that.
Hello, sir. Hello, sir.
Yeah.
Sir, can you like perform these operations on say one cardinal and then get to an ordinal in the next level of cardinal?
Of course. You see, wait, you said for ordinal.
Yeah, that is ordinals have a cardinal rate. I mean cardinal number rate.
But
so
a cardinal have ordinality, right?
Yeah, so I'm asking if you perform operations on ordinals of the same cardinality, like imagining the cardinality is infinite, can you get to the next level of cardinal?
Wait, we don't confuse between cardinals and ordinals. Okay, either you do ordinals, if you want to do something, a marriage between cardinals and ordinals, you have to tell me precisely what marriage you are doing.
No, sir, I'm saying if you operate, say, ordinals of the same cardinality, the same infinite cardinality.
Oh, yeah, okay.
Yeah. And is there a possibility that the resulting ordinal might have a higher cardinality?
Oh, no, it will not have. Okay.
Okay.
It will not have. Sure, very good, thank you. Yes. Okay, yes. Now I understand. If you take two ordinals which have the same cardinality, and if you add, will you go bigger? No, you will not. Okay, there is much theory about this.
Hello, sir.
Arithmetic. Okay.
Hello, sir.
Yeah.
So I didn't mean just two ordinals, but any collection of ordinals with the same cardinality.
Yeah, sure.
You'll still be in the same cardinality.
Oh yeah, not only two, but yeah, two. You will be still in the same cardinality regime. Okay.
Okay, sir.
The ordinals keep on changing, but not the cardinal.
Yeah. Okay.
Okay.
Yes, sir.
Okay.
So can you please repeat the definition of initial ordinal?
Okay. You see, so imagine ordinals as things standing in a line. Okay. An initial ordinal theta is such that if you take any ordinal below that, as sets, they are not isomorphic. They are not in one-one correspondence as sets. Okay? An initial ordinal is an ordinal so that if you take an ordinal below that, then the two are not in one-one correspondence as sets. Is it okay? Again, whenever you have a confusion, you go back to this example, you see. Okay. This is an initial ordinal, okay, omega, because the one below this. Okay. If you take anything below, that is finite, that can't be isomorphic to this. But this is not an initial ordinal, because if you took this one below this, then as sets up to this and this, they are isomorphic. Now, I should not do the isomorphism, one-one correspondence. Is it okay? So, I will tell you more about initial ordinals right now. Okay, so again, let me repeat. An initial ordinal is an ordinal alpha such that.
Sir, I lost my connection.
If you look at this set alpha, and if you take anything below alpha, namely if you take a beta less than alpha, look at all things up to beta, they are not in one-one correspondence. That is, alpha is a stage when a new cardinality starts. Is it okay?
Okay.
An initial ordinal is an ordinal where a new cardinal number starts. I did not want to say this in the beginning because then you might, confuse between ordinal, cardinal nonsense.
Okay.
Okay. Mix up both. So, ordinal numbers, you think of them as arranged in a line. An initial ordinal is an alpha in that line so that if you go up to alpha, the set has a certain cardinality, but if you stop anywhere before, it has a strictly lesser cardinality. Is it okay?
Yeah.
Now, for example, 0, 1, 2, etc. are all ordinals, which are also cardinals. Okay? Because the routine, I can't. Okay? Then, cardinals among infinite ordinals are called alephs. Okay? So, the initial ordinals, okay, which are infinite, they are called alephs. We don't call 0 as aleph. We don't call 1 as aleph. We don't call 2 as aleph. But omega is an initial ordinal, as I said. Okay? Because up to omega, there are infinitely many. But if you go anywhere below omega, there are only finitely many. Therefore, here, cardinality changes. This is called an aleph. And it is first aleph denoted by aleph 0. Okay? And you look at this omega, omega plus 1, omega plus 2, omega plus omega, omega, etc. Keep on going. First time, when the countability stops, that is called aleph 1. And continue. Next time, when that cardinality stops, it is called aleph 2, and so on. So,
Sir, does that mean, the cardinality up to, let's say omega, the set consisting of like 0, 1, 2, then up to omega, the cardinality is, let's say, aleph naught, and up to the, up to this like 0, 1, 2, then omega, then dot, 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 again omega plus omega, and this up to omega plus omega would be aleph 1 then. Is it so?
No, still be aleph 1. That's also countable. Look at omega plus omega, that is still countable.
That is countable, yes.
That is
yes.
Oh,
that is
countable. No, you don't get aleph 1.
Oh.
Okay?
Okay.
Omega plus omega plus omega, that's also countable. You don't get aleph 1. You have to travel too far. You can't imagine.
Oh.
Okay?
Oh.
You have to travel too far to get Aleph 1. And from there, you have to travel still further far to get Aleph 2. Okay? So, the best way to remember Alephs or initial ordinals or cardinals among these ordinals is a place where this set has a certain cardinality, but below that, it has a strictly smaller cardinality. Okay? It is a change point. These are the Alephs. Okay? Now, you can ask whether every set is in correspondence with some Aleph. Okay? Not necessary. Because that is same as saying it can be well ordered, right? If a set is in one correspondence with one of these Alephs, then that set can be well ordered because all these Alephs that I said are well ordered, right? Okay, there is a concrete example and so on, but there is no need for us to understand that. And here is an interesting question. Is ever infinite subset of R in correspondence with either omega or R? Okay. Real line is uncountable, all of you know. Yeah. And omega is countable, all of you know. Omega is a subset of R. If you take any subset of R, is it either in correspondence with omega, I take infinite set, or correspondence with R? We don't know. That is what we shall discuss tomorrow. The cardinality of R is denoted by 2 to the Aleph. Yesterday, Haimanti was telling you this. So the question is 2 to the Aleph equal to Aleph 1? Okay, we shall discuss more about this later, but right now we don't. What I want to do is the following. I want to describe transfinite induction and recursion. Now, you should think of these ordinal numbers as simply integers extended beyond your imagination forever. Okay? They are just like integers. There is 0 and 1, nothing in between. 1 and 2, nothing in between. 2 and 3, nothing in between, and so on. Okay? And then we have put omega at the end of the line. Then omega plus 1, nothing in between. Omega plus 2, nothing in between. Omega plus 1, omega, and continue. Okay? So exactly the picture I said, people standing in a line. Okay? Unending. But this is extension of your integers. What Cantor discovered is there are two things that you can do with, you are doing with integers, which you can do with ordinals. Okay, that is very important. What is the thing that you do with usual integers? So let us first see that before you confuse with ordinals. Suppose you show there is a sequence of statements, one for each integer. Okay, S0, S1, S2, S3. If you know S0 is true, assuming that S0, S1, S2, Sn is true, you show Sn plus 1 is true, then you can conclude for all n Sn is true. This is called mathematical induction, right? When you want to prove a sequence of statements, you say, okay, I will prove it by induction. Of course, usually you don't start with S0. I started with S0, but that's okay, don't worry. S1 is true. Assuming you have proved up to n, you prove for n plus 1. This is called mathematical induction. And why should you accept mathematical induction? It is because of the following theorem. Suppose A is a subset of omega. Okay. I want you to understand omega consists of 0, 1, 2, 3, 4, 5, 6, etc. It is that set. Okay. Assume 0 is in this set, and if 0, 1, 2, k are in this set, then k plus 1 is also in this set. There are two hypotheses. Then the conclusion is A is all of this set. Okay? That is called mathematical induction. Of course, when somebody says mathematical induction, they don't mean this, they mean this. But doesn't matter. We agree to this because of this. Okay. Why should we accept it? Suppose you say A is not all of it. Then you take the complement, it is not empty. Look at the first point. That gives you a contradiction. The first point cannot be 0 because 0 is in A. And if the first point is K, you told me that being the first point of A complement, 0, 1, 2 up to K minus 1 are in A. Therefore, K must be in A because of this. Therefore, this is essence of the induction. And from here, you get your usual induction. Okay. There is something called transfinite induction. This is precisely the same thing extended to ordinals. Suppose alpha is an ordinal number and A is a subset of alpha. Earlier, we have taken alpha to be omega. A is a subset of omega. This is for general. Suppose 0 belongs to O. This is error. 0 belongs to A. Yeah. Okay, this is error. Suppose 0 belongs to A. Okay. And if there is an ordinal beta in your discourse, if for every gamma smaller than beta, gamma is in A, then beta is also in A. Then my conclusion is A is equal to alpha. Okay. Now,
Sir, please repeat this.
Yeah, I will repeat. Suppose you take an ordinal number alpha. Okay. And here I replace omega by alpha. Okay. Replace omega by alpha. A is a subset of the ordinal number alpha. Suppose 0 belongs to A. Suppose, now I can't say dot, right? Suppose beta is an ordinal within alpha, just as K is in omega. Okay. Beta is an ordinal in alpha. For every gamma less than beta, if gamma is in A, then beta is also in A. Two hypotheses. I am saying exactly the same two hypotheses. Please remember. The 0 is in your set. If everything smaller than a beta is in your set, beta is also in your set. You see, forget about K, K plus 1, etc. Everything below K plus 1 is in A, then K plus 1 is in A. That is what it says.
Yes, sir.
Now, what I am saying is, if everything below beta is in A, then beta is also in A. In that case, A is the entire alpha. Okay?
Yes, sir.
You have a subset of an ordinal. If the initial point, namely 0, is in your set, if whenever all things below some nonsense is in your set, then that nonsense is also in your set. Then your set must be all of alpha. Okay? Exactly the same thing. Is it okay?
Yes, sir.
Exactly the same. Replace omega by alpha blindly. Okay? But only thing is, don't say K, K plus 1. Okay? If everything up to beta is in A, then beta is also in A. Okay? That's it. Then A is same as alpha. Proof is very trivial. Okay? If A is exactly the same proof, if A is not alpha, look at the smallest point which is outside A and so on. Okay?
Sir?
Yeah.
Then, I mean, how is the transfinite induction different from the mathematical induction as, I mean, the normal case?
Mathematical induction is only for omega.
So natural numbers.
Yes, natural numbers. Finite, okay? This is the transfinite. Trans means beyond finite. That's all. This is induction. Okay? This is simply induction. So both are induction. That is only for finite. This is transfinite, beyond finite. Okay?
So how does
exactly the same thing. Therefore, I will not mention. Yeah. Yeah.
I mean, how does it? How is it beyond finite in this definition?
Wait a minute.
You said the
Wait a minute. Read. What did I write here?
Alpha be an ordinal.
Alpha. Okay. Did I say it is 0, 1, 2, 3? Can it be omega plus omega?
Yeah.
Then
Yeah. Okay.
that's it. That's
Yeah,
it.
yeah.
Alpha can be omega plus omega. Alpha can be omega plus omega plus omega. Then is it?
Yeah. Okay.
Okay.
Mhm.
And now I will mention another thing which is also very important, that is transfinite recursion. You see, these are things that you do in practice. Okay. You want to define a function, for example, factorial n. One way to say is, okay, factorial e is 1 into 2 dot 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 n, multiply. No good. You define it by induction. You say factorial 0 is 1. If I have defined factorial up to n, I define factorial n as the previous thing multiplied by n. Correct? That is how you define factorial n. Similarly, you see even elementary. For example, how do you define 2 power n? Okay. You say 2 power 0 is equal to 1. If 2 power k is defined, then 2 power k plus 1 is 2 power k, you have already defined, multiplied by 2. That is how you define. These are all defined by recursion. Okay. And incidentally, in your recursive functions also, you come across this. Things defined by recursion. So, then, there is a function which satisfies your conditions. Okay. That is, there is a function factorial n defined for every n. You might ask, why do you need a theorem? Yes, of course, you need a theorem. Because we have not defined the function outright. Sin x outright defined, cosine x outright defined, e to the power of x outright defined. But factorial n, no way. Okay. So that is why you need a theorem. And similarly, there is a transfinite recursion. Suppose alpha is an ordinal, and you want to define a function on alpha into a set x. And you already have a function g defined on transfinite sequences of points from x. Then there is a unique function f on alpha such that f0 is the given quantity, and for every beta less than alpha, f beta is g at whatever you have defined so far. Okay, that is it. Now, I might come back to a proof of this, but to tell you the importance of this, let me go a little ahead. Then, if there is time, I will come back to this. The little ahead is simply the following two things that I have left earlier. Namely, I showed that well-ordered principle implies axiom of choice. You can select the first point from every non-empty set. I shall now show axiom of choice implies well-ordering principle. Okay? If you tell me axiom of choice, then you can well-order any set. Why? W be a non-empty set. I am coming to this because you will see this recursive definition, which you may think abstract, okay, acting here. Fantastic. W is any non-empty set. F be a choice function for the collection of non-empty subsets of W. Okay. I define GA as f of A complement if A is a subset of W, but A is not all of W. If A is not all of W, then A complement is not empty. Therefore, the choice function associates a point of A complement. Okay? That is my G. Okay, here is my function. I am defining a function on W to an ordinal. And this function will be one-to-one on to an ordinal. Therefore, you can well order this. I have set up a map from the given set to an ordinal, which is one-to-one. Therefore, whatever drama goes on the ordinal can be brought back here. The well order on the ordinal can be brought to W. That is the well order. Okay, how do I define? F of 0 is G of empty set. What is G of empty set? the thing selected from whole space. And what is f of 1? G of the earlier thing, that is f of f0 complement. Okay. So in other words, I am defining for every ordinal alpha up to whatever f of alpha. Okay. And that is from ordinal to W I am defining. I am not defining from W to ordinal, but ordinal to W. Again, let me explain the idea. Your choice function already gave you from every non-empty set a point. Okay. Take the point from W. That is f of 0. Take the point chosen from this f0 complement. Okay. In other words, at every stage, if I want to define f of beta, if I have defined f for all previous things, I look at that set of all the previous things, look at the complement, and see what your choice function tells you. That is f of beta. Okay? So f of 0 is what the choice function told you for whole space. What is f of 1? Delete this point. In other words, look at the complement of this. Whatever your choice function told you, that is f of 1. And what is f of 2? Remove f0, f1 from your set, W. Whatever the choice function gave from that is f of 2. What is f of 3? Remove these things. If you have defined f of 0, f of 1, f of 2, f of 3, etc., you can see that these are all distinct, one to one, naturally. If f0, f1, f2 defined like this by using your elementary usual recursive procedure, gives you all of W, finished, no more. But if it does not give all of W, then I continue further. Okay? F of 0, f of 1, f of 2 I have defined. All these things still left over something from W. So f of omega is a point from what is left over given by your choice function. If f of omega gives you all of W, then over. Otherwise, if still something is left over, I define f of omega plus 1 as what your choice function gave in the complement, that is, in what is left over. So I define a function from ordinals to your set W. This is intuitive idea made precise, and because you have to communicate, you use notation. But otherwise, the well-order prescribed is as follows. You fix once and for all a choice function for non-empty subsets of W. Okay? Zeroth point is selected from W according to this machine. Okay? Your choice function is the machine. At any stage, if you have not completed all of W, look at what is remaining and see what your choice function gives you. That point is the next point. In other words, you arrange all points of W in a line like this. That is the well order. That's all. Okay. And because we want to do this, we do not know where the process stops. Factorial n, 2 power n, etc. They stop at the integers, but these things may go on. That is why we need transfinite recursion. By the way, okay, I'll go to that later. Let me show the other thing also. I showed that John's lemma implies axiom of choice. Now I shall show axiom of choice implies John's lemma. Okay? And because I already showed you axiom of choice implies well order, I can as well assume that well ordering principle implies John's lemma. So what I do is the following. I first well order my partially ordered set. Please remember, what is John's lemma? you have a partially ordered set. Every chain has an upper bound, then there is a maximal element. What I am going to do is the following. Okay, I fix a well order on my partially ordered set. I take a point from my partially ordered set. If there is nothing bigger than that, this is a maximal element. Done. But if there is bigger than that, that I shall define f of 1. Okay, f of 0 is the first point. F of 1 is the next point, which is bigger than this. Okay, if there is nothing bigger than f of 1, this is the maximal element. If there is something bigger than f of 1, then I pick the least element. Because there is a well order, I pick. So this way, I keep on picking least elements if anything is left over. If nothing is left over, then I got a chain which is maximal. This chain has an upper bound. That will be maximal element. Okay? Because if it is not maximal, if there is something beyond that, then you could not have said that your process stopped. So that is this one. So the recursion is simply, by the way, the proof of recursion is written down there, but proof is also just like the usual proof, okay? Mathematical induction. If you are familiar with the proof of defining functions recursively in usual mathematics, exactly the same proof, and you use the well-ordered property. So I just leave it at that. Okay, that completes our discussion about axiom of choice. And tomorrow we shall discuss about axiom of choice and continuum hypothesis. You can ask me any questions now.
Hello, sir.
Yeah.
So usually when we talk about classes like in Bernie's Gödel set theory and all,
yeah,
they treat classes like they make some different definition for classes and they treat them
exactly,
differently.
Exactly.
So, yeah, so I was asking, instead of doing that, can you treat true and false as a new truth value and then
Can
you treat can you treat true and false as a new truth value, like the third truth value, and then can you treat classes? Because usually when you talk about classes, contradictions happen, right? That is, you get some statement is true and some statement is false also. It cannot happen, right? In our usual set theory. So I was asking if you could make the pre-valued logic and.
You see, in usual set theory, contradictions don't happen because of classes. Because of self-referential sentences. You see, that is the important thing. Okay, self-referential things.
Okay, sir.
Anyway, yeah, but I don't know. You see, there are several ways, but in Gödel, Bernays and so on, you don't start with the formula nonsense that I said in ZF. You start with the classes also. Sets and classes, two different kinds. Yeah.
Any other questions from the audience?
Well, yeah, I can ask a question. So yesterday there was a question, I think from Shamik on YouTube Live.
Yeah.
That how do you actually talk about models of set theory? Because the way I defined it in predicate logic.
Yeah.
Yeah. So I said that the universe of it has to be a set. So
yeah.
There is a notion of external set and then internal set. So maybe you can explain it better. So I pose the question to
we shall
you.
do that tomorrow. Tomorrow it will come up discussion. But however, right now I can tell, you see, the whole point is this. One has to understand the philosophy. The philosophy, again, it will come back tomorrow. It is because you asked, I am telling right now. You see, either you say, I believe that ZF is consistent. Therefore, I work in ZF plus consistency of ZF. That is, I work in the theory ZF plus ZF as a model. Okay, I work in that model and then do my works. Therefore, there is a model there. I continue. Or you can say, no, I don't agree to that. Then you can say the following thing. What are we trying to do? We are trying to do whether a certain collection of sentences, okay, is consistent or not. Now, if you think it is inconsistent, finitely many of these will lead to a contradiction because our proof is finite in length.
Yes.
It is a theorem of set theory that given any finitely many axioms of set theory, there is a model satisfying these finitely many axioms. It is a theorem in set theory. Okay. Therefore, if you say that somebody found a contradiction, I will say what are the finitely many axioms you did to use to arrive at the contradiction. Then I get a model where these finitely many are true. And obviously, you could not have got a contradiction because it's a model. Okay, so that is another way of looking at it. There are two ways of looking at it. Yeah, right.
Okay, thanks.
Hello, sir.
Yeah.
Sir, is there any other area of mathematics that uses proper classes and not just sets?
Proper classes?
Yeah, that actually uses proper classes, like the usual.
Not that I know of. In functional analysis and so on. You see, the whole point is this. I am not familiar, first of all, with many areas of mathematics. There is one area called category theory and so on. So you look at the category of all topological spaces. Okay?
Okay, sir.
I am not at all familiar with category theory. But if you are looking at the category of all topological spaces, then that is definitely a class, not a set.
Okay, sir.
Okay? So category theory is one place where they use.
Okay, sir.
Yeah.
May I ask a question? I mean, is this set theory very much depends on the linearity, that inclusion and also the first element, if I am right.
Yeah,
is there something
but every set, yes. Regularity.
Is there something like a non-linear set theory?
No. You see, no. First of all, linearity is not needed. You see, only ordinal, if you take an ordinal, then the relation belonging to is linear on the ordinal.
Right.
That's all, but not on all sets. As I said, you should imagine the entire universe like a cone. Okay? And
but also it looks like one-dimensional set theory. I mean, is there something like
only ordinals are one-dimensional, but the set theory is fully like a cone. You see?
Okay.
Yeah.
Okay.
You take any collection of sets, their power set, their power set, their power set, it goes on and goes on, expanding. Okay?
Right.
So only the ordinals are like a straight ray. Okay?
Right. In the cone. Yeah.
So imagine a big cone with a vertex and the middle line, okay?
Yeah.
The ordinals. And all around it are plenty of sets. So there's no linearity.
Sure. Thank you.
Thank you so much for the lecture, sir. We'll take a break of 10 minutes and then we'll come back for the tutorial session. See you then.
Thank you.
Yeah. Since there are 5 minutes to go, if there are any questions from the participants, they're welcome.
Swapnil, you seem to have an aura.
Okay.
Yeah, like your video will show some light around you.
Yeah, actually, I'm sitting near a window, so maybe that's it.
Right.
Yeah.
Okay. We can wait. Yeah, Sujata, you want to say something right now or wait until?
Whatever you prefer. Like, I don't have any.
Yeah, I mean, still, yeah, I don't think there will be too many more participants than 40. You can make an announcement.
Yeah. So let's wait till 4 at least.
Okay. Yeah. 1 more minute to go.
Sir?
Yes.
So what's the difference between free variable and bound variable?
Yes, a bound variable is always associated with a quantifier, there exist or for all. Whereas a free variable is not associated with any quantifier, and that is why you can assign values to it. You cannot assign values to a bound variable unless you want to interpret it.
Okay. I mean, can you give an example?
Yeah, sure. So, for example, I mean, this RXY that I have here, yeah, there is no quantifier. X and Y are both free variables. So if I want to verify the truth of R in a structure, then I have to assign values to X and Y. Yeah, so I have done that here, 5, 6. Whereas if my statement was something like there exists Y, R, X, Y.
Can you repeat that?
There exists Y, R, X, Y. Now this is a formula in one variable. Just X. Yeah, there exists Y, R, X, Y. Then I can only check the truth of that at 5, let's say. I cannot put two values in. Yeah, I cannot substitute 6 for Y if there is a quantifier. So in that case, the variable Y is bound variable and variable X is a free variable.
Okay.
Yeah, Sujata, I think you can.
Amit, because I actually need to share the screen.
Sure, I can stop.
Yeah. So let me share the screen and then maybe talk about this.
Yeah.
So can you all see my screen and can you hear me? Am I audible?
Yes, ma'am.
Yeah. Thank you. So hi, this is Sujata. Just to introduce, I'm a logician who is working in the Indian Statistical Institute in Chennai. So what I would like to share with you is something regarding this association for symbolic logic. So I'm sure in the last 5 days you have got introduced to both logic and set theory. And you will have some more introduction to it here, and maybe it's beyond the school in some other places as well. So what I would like to do is introduce to you to like kind of the what is kind of the work that is going on in here currently, and how would you get introduced to such work, or how can you read about this work. So in that sense, I would like to introduce to this Association for Symbolic Logic, which is kind of the parent institution of for the logicians from all over the world. And they hold an event like Logic Colloquium. This is a picture from the Logic Colloquium 2019, which was held in Prague. And they hold this kind of events every year. And there are other meetings as well, which are kind of ASL associated or ASL sponsored meetings. So there is a possibility of becoming members of this association. Now, the obvious question is, what will you get by becoming a member of this association? So let me now just show you this kind of journal. So if you become a member of this association, ASL publishes two like top journals in logic. One of them is in mathematical logic, which is known as the Journal of Symbolic Logic. And the other one is the Review of Symbolic Logic, which publishes work in philosophical logic as well as non-classical logic and other kinds of logics as well. So these are the two things. And then you get, of course, there is no travel all around, but there are student travel awards if you become a student members to ASL sponsored meetings. And for now, since there is no travel going on anywhere, ASL kind of supports registration as well to certain meetings if you become a member. Now, how do you become a member for this Association for Symbolic Logic? So let's move on there. So for individual members, the main thing that is of interest to you is like this outreach members. Like what is happening, like for countries like India, who are from the developing economies, the Association for Symbolic Logic, they can be members of this association, invites membership to the people from countries like India, and they can apply for up to 2 years of free membership. And to apply for this free membership, when you will get all these journals and other informations from association as well. And to apply for email free membership, you just need to email your full mailing address and professional affiliation to the ASL membership committee, which is given by this. And you do not need to fill up any forms or anything, just write, send in your address, mail, and your professional affiliation to this email address. And then you can become a free member of this association for 2 years, for the next 2 years. So since the year-long, the members can be, new members can go in from January 1 to 31st December for basically the calendar year. So I think now is the right time. If you're interested, now is the right time to write to this email address and become members of this association. Okay, thanks a lot. And thank you, Amit, for giving me the floor to discuss about these things.
Thanks, Sujata. I can say that I have been a member of ASL in the past, and I have utilized their travel funds to travel to Italy. So it was definitely convenient.
But even without these travels now, they can actually register to certain conferences.
Yes.
And if it's interested, you can also look at the journals, articles, and but not for the students now. But if you're a PhD student, those might come in handy.
Thanks, Sujata.
Thank you.
Yeah, let us.
Good evening, everyone. To welcome to today's tutorial session, I invite Dr. Amit Kubey to conduct the same. Sir, please.
Thank you, Swapnil. This is the last tutorial session and also my last session in this school. Yeah, I mean, before I proceed to the tutorial, I would again like to ask you the same question, whether you have any questions about everything that I have said so far. Okay. In that case, we can go ahead and try to do this. So I have tried to include some interesting exercises here Let's see. So can you find a sentence in the language with only one binary relation symbol such that it is true in the integers but not true in the rational numbers? Yeah, anyone?
So
Yeah,
we
Ujjwal?
can have this sentence.
Mhm.
There exists X and Y. I mean, there exists X, there exists Y.
Correct.
Such that X. Okay. Before I state this sentence, I'll introduce a new connective. I mean, I'll introduce a new binary operator saying X less than Y, if and only if X less than or equal to Y and X not equal to Y.
Not equal
I mean,
to Y.
negation of
Okay.
negation of X equal to Y.
Okay. Okay.
So now the sentence is there exists X, there exists Y, such that X less than Y, and for all Z, Z less than or equal to X, or Y less than or equal to Z. Like essentially what
X
I
less
want to
equal Y and Y. Oh, sorry.
Z,
Right,
I mean X is less than Y, and for all Z, Z less than or equal to X, or Y less than or equal to Z.
Correct. Correct. So you are
like
describing
consecutive
negation of some famous property. What is that?
And density.
Exactly. Exactly. So Q is dense, whereas Z is not dense. Like, yeah. So every element has a successor. Every element has a predecessor in Z, whereas the same property is not true in rationals. And yeah, so that is a distinguishing characteristic of Z and Q in this language. Yeah, we are mainly worried about how a particular language is powerful or it can't do certain things. Okay, so any questions about this, or do you have any other answers apart
Sir, I
from
couldn't
density?
understand this.
So in rational numbers, between any two rationals, there is a third element. Yeah,
Yes,
for
sir.
all X, for all Y, there exists a Z such that X is less than Y, less than Z, and Z is less than Y. So he just described the negation of that, and that sentence is true in Z, whereas in Q that is not true. Yeah, Z, the order on integers is not dense, whereas the order on rationals is dense. Yeah, negation of having an inverse. Okay, Mayank, which inverse, multiplicative inverse cannot be expressed? Yeah, cannot be expressed in this language. It is less equal. Yeah, we are talking about expressive powers of languages. So less equal cannot talk about inverses. It cannot talk about multiplication or addition. Yeah, that is the beauty of it. We are going to analyze the structure step by step.
Sir, also, are we allowed to introduce notations?
Which notation?
Like he introduced, I think, equal to. So,
No, equal to is always there. We have described that in our meta language, if you remember. Yeah, on the first day itself. Yeah, equality symbol was already present in the meta language. So he did not actually say anything new.
Okay.
He just defined that X is less than Y if X is less equal Y and not X is equal to Y. So he just described the formula. Yeah, you can, of course, use another formula in a bigger formula. Yeah, that is definitely allowed. Okay, so do you can you tell me a sentence which is true in Q but not in R when you are just considering the ordered structures? I mean, some property of rational numbers which is not a property of real numbers.
So multiplication is always rational.
Multiplication is always rational. Is there any multiplication in L odd?
No, so sorry.
No. Anand, so least upper bound property, LUB property, yeah? So is that property expressible in first order language as a first order formula? Yes.
I don't think there is a sentence.
There is a sentence. Okay. So Ujjwal doesn't think so. Dhruv wanted to say something.
Sir, like the property I'm thinking should be that cuts, like initial segment. So, for example, that root, like rationals less than root 2. There is no
Okay.
representative
Okay.
for that initial segment.
Okay. 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 So you are using something, but actually what you are describing, yeah, I mean, I will come to that in a minute, but that is not a sentence by itself.
Yeah, I'm trying to build a sentence out of that property.
Right. Then Muthukumar says countable. Can you say something is countable as a first order sentence? These are interesting questions. Yeah, can you please try to do that, Muthukumar?
Sir?
Yes? Yes, Muthukumar? You are unmuted. You can speak.
Sir, I was just trying to think out of it, but I could not get the exact answer.
Okay, can you at least explain your efforts? Okay, Dhruv or Anand, do you want to say something more after a bit of thought? Okay, so let me tell you that there cannot exist such a sentence. Yeah, a first order sentence is a finite formula. In a finite formula, you cannot express something like countability. You actually cannot capture cardinality. Okay, so this is very interesting. We will do that thing very soon. Yeah, that property. So you cannot capture that it is finite. You can say that there are exactly n elements. Yeah, you can say that, but you cannot say that the set is finite. There is no first order sentence which says that your universe is finite. Then there is no first order sentence. So what did Dhruv say? Yeah, he wanted to capture the notion of cuts. Yeah, so for cuts, what do you need? You need that there is a sequence which is Cauchy, but not convergent. Now, how do you express that a sequence is Cauchy? You have to use quantifiers over something else. You will have to say that for all
neighborhoods nearby.
All neighborhoods nearby, or you have to say that for all there exists an n, yeah, such that there exists a capital N such that for all n and m bigger equal that capital N, distance between xn minus xm is less than epsilon. Yeah, for all epsilon there exists something like this. So for all epsilon is still okay. Yeah, but there exist elements of the sequence that cannot be done. Yeah, because that is quantification over that. You want to talk about a particular sequence at that time. So there is a bypass for this. Yeah, I mean, I'm just going to say this once, that you can study types in logic. Yeah, types are precisely, I mean, what are they? They describe infinitely many properties together, like they are infinite collections of formulas. And then you can ask whether all these formulas together are satisfiable. Again, compactness, etc. comes into picture, and then you can generate, I mean, using types. Yeah, closing under witnesses for types will give you R from Q. Okay, so there is a formal procedure, but of course beyond the scope of our current scenario. But it can be done, but not using a single sentence. You have to use multiple formulas at the same time. A cut is nothing but a type. Okay, as far as first order language is concerned, you cannot distinguish between them.
Sir, how do we prove it?
What?
How do we prove that there is no such sentence?
Yeah, I mean, you try to write down all sentences, and so basically, yeah, the theory of Q less equal. I will do that at the bottom. Yeah, here this is the last question. Let TDLO be the L-OR theory of dense linear orders without endpoints. Yeah, so theory of dense linear orders. So Q is definitely dense. R is also dense. It is linear. Both of them are total orders, and it doesn't have any endpoints. And so actually theory of Q can be axiomatized by this theory. Yeah, that it is dense, it is linear, and doesn't have any endpoints. So therefore, this TDLO is a complete theory because it is theory of Q. And R is also a model of that. And of course, then you cannot have anything more. Yeah? If you have a complete theory already, you cannot add any extra axiom.
Oh. So this is an argument which tells that, oh, there is no such sentence.
Yes, there is no such sentence.
Wow.
Yeah. Okay. So this is known as elementary equivalence. Yes.
How did you say that there's no such sentence? You just, using the allowed.
So the theory of dense linear orders without endpoints has a model. And what is that model? It is Q. And actually, theory of Q can be axiomatized by using just these few sentences, that it is linear, it is dense, and there are no endpoints. So that those sentences together axiomatize Q. Therefore, it
and
is.
R also.
And also R, yes.
Okay, yeah.
And
both, true for both.
True for both of them. And because it is the theory of Q, yeah, TDLO is the theory of Q in this language, theory of a particular structure. Therefore, it is complete. And you cannot add any extra sentences. Like R is also a model of this theory, and you cannot add anything extra. So they are elementarily equivalent, which means their theories are exactly equal. They satisfy the same sentences.
Okay.
Yes. Okay. Third one.
Sir, could you explain the role of types once again? Types.
Yes. So types are infinite collections of formulas in the same variable set, finite variable set. And cuts, as we say them here, yeah, to construct real numbers, we have cuts. Like for example, √2. There is a sequence of rational numbers which is Cauchy sequence, but it is not, like Q is not complete. So you would like to add an element which witnesses that this type is satisfied. Like for very formally speaking, you do this. You take one increasing sequence to √2 in rationals and one decreasing sequence to √2 in rationals. Yeah, I'm trying to add √2 to my language, to my structure. I will say xn is the increasing sequence, yn is the decreasing sequence, and I describe the formulas in variable z, that x1 less than z less than y1, x2 less than z less than y2, and all of them together. Yeah. So consider this infinite collection. And I have added, let's say, so many constant symbols in my language to which are interpreted as x1, x2, xn, y1, y2, yn, and so on. I can add as many constant symbols as I like. So all of these are constant symbols. Now you observe this collection of formulas. This is finitely satisfiable. Yeah, because at a time you are only describing finite number of equations. So whatever is the largest n in that collection, you have taken, like, this is the first intervals, this second interval, third interval, and you are just choosing finitely many. So let's say this is the interval, and in that you can definitely find a rational number, which means in rationals itself, this whole this finite set of sentences has a model. Okay, so by compactness, it has a model where like the entire set of sentences also has a model. So therefore we have a model where there is a name for root 2. And that is precisely what we do for obtaining real numbers from rationals.
Okay, sir. Thank you.
Okay, you're welcome. Right, any other questions? So this cut construction, yeah, of reals is nothing but using types and compactness, really speaking. But it is not presented like that. Anyway, so let's go to the third one. So L rings. Yeah, now you have plus dot minus 0, 1. Yeah, these are the symbols. So can you tell me a sentence which is true in complex numbers but not in real numbers?
Sir, can I try?
Yes.
Okay. I'm defining in the complex numbers. So there exists W such that W dot W equals X minus Y.
W dot W equals?
X minus Y. Yes.
Oh, X minus Y.
Yeah. I mean, minus is there, right?
Okay. What will this achieve? Like this is not a sentence.
Okay.
You should bound the variables X and Y.
Okay.
This is a formula. Yes.
May I try? I don't think there will exist such a sentence.
No, there will exist definitely. Yes, somebody else was saying like Soumya. Yeah.
Let me complete what I was saying.
Okay.
And I mean, along with that, I would add, I mean, and X less than Y.
Yeah, fine. But still, you have two free variables. X and Y are not bounded. That is a problem. Yes, Soumya.
So for all x, there exists omega such that x equals to omega square.
For all x, there exists an omega.
Such that x is equal to omega square.
So every element has a square root. Yes. Okay, good. Yeah. So Anand has also said something similar. Yeah, there exists x such that x square plus 1 is equal to 0. So he's just saying that minus 1 has a root. Yeah, so that is a simpler way of doing this. Yes. And you said that every element has a square root. Yes, that is also correct. So there are many sentences which are true in complex numbers, but not in real numbers. I mean, in particular, what is happening that all even degree polynomials don't necessarily have a root in real numbers. But in complex numbers, they do. Because what is the main property here?
C is algebraically closed.
Algebraically closed, yes. So fundamental theorem of algebra. Fundamental theorem of algebra states that every polynomial in one variable with integer coefficients has a solution in complex numbers. But that is not true with real numbers. So this is a very, it's called fundamental theorem of algebra. But yeah, I mean, that sentence can be expressed in terms of, I mean, that is a sentence in this language and we can take it as a distinguishing property. Okay. So fourth one, in LGR, in the language of groups, means one binary symbol and one function symbol.
Sorry. I thought it's similar to the first one, but I'll have to think once again if that's true.
Okay. Yes, anybody? Dhruv?
For every x, there is a y such that y plus y equal to x.
Very good. Yeah, so this is known as divisibility. Yes, so divisibility is a property of real numbers or rational numbers. That is not a property of integers. Yeah, you should not use multiplication. It is not given.
Sir, if you replace Z by Q, then is there a sentence?
Z by Q. Let us see.
Sir, we saw that it's not possible, right? I mean,
That
you
was for
would be.
less than equal.
No. That was for
Okay.
less than or equal to. This is about additive group.
I don't think it will be possible here as well.
So we are doing we are taking a subset of that set and performing the same operation and implying that subset has the truth, but the superset doesn't have that truth. Well, so I
Yeah,
don't think
Nitish,
it will be.
what exactly you want to say?
So integers are subset of real numbers, right?
Yes.
So if something that is with the same operations, if it is true for integers, then it's obviously true for all R. So I don't think there will exist a property.
No, but we just described, yeah, divisibility.
So I
From
didn't
Z
get it.
to R. Huh?
I he wanted to say the either way. Like if it is true for R, then it must be true for the subset.
Okay. But that is, yeah, I mean, that is usually not true.
I got my confused. Right.
Yeah, that is usually not true. Yeah. If there exists a witness for the existential quantifier in the larger structure, then that doesn't necessarily mean it exists in the smaller structure. Yeah, Deepanvita. So for example, x square plus 1 has a root in C, but it doesn't have a root in the smaller one.
Yes. Okay, so it need not be true in either way.
Yes.
Okay.
I mean,
So
all of you are talking about a notion that is known as a homomorphism of structures, or a more specific version of that is known as elementary embedding. It is an embedding between structures, yeah, a one-to-one map between structures, such that for the smaller structure, all the operations are the induced ones from the larger structure, and the truth of formulas is preserved both ways.
Yes.
That is an elementary structure. Yeah, I mean, yeah, for Q plus 0 and R plus 0, I believe that there is no such sentence. Yeah, they will be elementarily equivalent. But yeah, I don't have a proof right now. Yeah, Deepanvita, you want to say something?
No, sir, not yet.
Okay, Soumya?
Sir, but the example that was given was for all x, there exists a y such that y plus y is equal to x.
Yes.
So this is true in R, but not in Z. But we want something that is true in Z and not in R, right?
Negation.
Just take negation. Yeah.
Okay. Yeah.
Yeah. But for Q and R, I don't think we can find a sentence.
Okay, sorry.
Sir, I didn't understand the divisibility argument. Can you explain it?
Yeah, so for example, does there exist a y such that y plus y is equal to 1?
In Z?
In Z?
No, there isn't.
No. So, but that is true in real numbers. Yeah, every number can be divided into equal parts.
But sir, we are looking for a statement that is true in Z and not true.
Yeah. So you say that there exists negation of this sentence. Yeah, there does not exist. Yeah. So you take the formula for all x, there exists y such that x plus x, y plus y is equal to x, and take the negation of this. That is true in Z, but not true in R. Yeah. This is always simple. Okay. So fifth one now.
So there exists x1, x2, etc., xn, such that we inside the quantifier we just do a conjunction over xi equal to xi.
Xi
equal to xi.
What will that achieve? Xi equal to xi is a tautology.
Yeah, but what I have said is that there exists x1, x2, etc., xn. So I have asserted that there are at least 10 elements in the.
Yeah, but when you interpret them, what is the guarantee that they won't be interpreted as the same element of the universe?
Correct. Okay, so I'll along with this, I'll do a conjunction that xi. No wait.
Xi.
I mean,
Negation
overall the indices less than, I mean, overall the indices from 1 to n, ij, such that I is not equal to j, I will do a, I'll do a conjunction of xi not equal to xj.
Exactly, exactly. So there exist n distinct elements. You can write that. Yeah, there exists x1, there exists x2, there exists xn, such that conjunction of negation xi equal to xj. Yeah, xi is not equal to xj for different distinct I and j. This is a finite length formula. Yeah.
We have to also put this, right? Xi belong to A, like where A is the.
You don't need to. Yeah,
Why?
that is the thing. I mean, how do you interpret? So the formula
integration
says there
goes
exists x1, there exists x1. Yeah, so it is a bound variable.
Yes.
And that bound variable has to be interpreted as an element of the set.
Yes. But
so you don't need to say that, and you cannot actually say that. Yeah, you should understand.
But we have
you cannot say,
in
because
sentences.
A is a structure. You have no control over structures. In sentences, you are not allowed to talk about any set.
And in language of L set, there is no relation also, right?
Yeah, there is nothing. Yeah. So this formula describes that it contains at least n elements. You can actually describe that there are exactly n elements. So somebody else should give it a try right now.
Sir, can you explain the meaning of the question? I couldn't understand.
So the question asks for a sentence which describes that there are at least n elements in the universe. And we have described that. We said that there are n elements and they are all distinct. And anybody with an answer for size of A is equal to n?
Sir, I think in addition to what he said, we can add this like at least n, and then we write and for all x1, x2 up to xn plus 1.
You just need to argue about that xn plus 1 now. You don't need it.
Sir, xn plus 1 equal to some xi, such that like.
What is x1 plus 1?
Xn plus 1.
Xn plus 1, yes.
Yeah. It is equal to some one of those elements.
Correct. So for all xn plus 1.
Xn plus I.
Yeah, for all xn plus 1, the disjunction of xn plus 1 is equal to xi, where I runs from 1 to n. Yeah, so that will describe that every element is one of these. We first asserted that there are at least n elements, distinct elements, and now we are saying that every element is one of these. Yeah, so yes, that's true. Okay, good. So we can describe that there are at least n, at most n, and exactly n. Yeah, so we can capture a particular finite cardinality. Okay, let us go ahead. Like I already said something about this. The language of Zermelo-Fraenkel set theory is just this belonging relationship. And TZF is Zermelo-Fraenkel set theory. And here there should be a not, yeah? A statement that is a sentence that is not a logical consequence of TZF and whose negation is also not a logical consequence of TZF. And this shows that TZF is incomplete. So such a statement is, anyone? What is such a statement? Deepanvita?
Undecidable.
Axiom of choice.
Axiom of choice, continuum hypothesis. Yeah, all of these are sentences which can neither be proved nor be disproved. If you replace this by PA, Yeah, piano arithmetic. Then what is the statement? What is such phi? You learned that in the first lecture today. It is consistency of the piano arithmetic. Yeah, you cannot prove from piano arithmetic that it is consistent, and you cannot disprove that it is consistent. Okay, I think you need some time to revise that material. Yeah, I know, I have been to schools in my student days, and they are really very intense. So you need a lot of effort, and yeah, you will sleep very little if you are being
Sir?
serious. Yes.
Sir, so in the thermal of Frankel set theory, I don't know. I mean, I don't know all the axioms. So if I assume axiom of choice, so that cannot be described using first. I mean. Okay, there cannot be one such
Axiom
sentence.
of choice is a sentence of Zermelo of this language.
Okay.
Yeah,
So,
it is a sentence. Yeah.
Yeah, we cannot prove or disprove it. Why? Because why? Why?
Because of its independence from other axioms. You will see more about that tomorrow.
Okay. Okay.
Yeah, in B.V. Rao's lectures. Yes. Right. So let us go to the 7th and the final one in this lot. That some sentence, this is easy one, some sentence which is true in the semi-open, semi-closed interval, but not true in the closed interval.
So,
yeah.
I just thought about this, not sure it will work. It does not exist an X such that before I state the sentence, I'll define the binary operator less than or equal to, saying that X less than Y if and only if X less than or equal to Y, if and only if X less than Y or X equal to Y. And now what I'm saying is there does not exist an X such that for all Y, X less than or equal to Y.
Okay. Yeah, that is true. Like you are capturing the minimal element. There doesn't exist a minimum element here, and there exists a minimal element.
Yeah.
Yeah. So that's all. Good. Okay. Now second question. Yeah, I have given it a special status. It's not in that list. Find a formula phi xy in the language of rings such that for all a, b, and z, phi is true in the integers at AB if and only if A is bigger equal B. So one of you have solved this, one of the others have attempted only. So has anybody else got the solution? Or want to give it a try? Well, today I'm going to ask you a stupid question for a poll. Yeah, you just have to answer, are you here? Yes or no. I'm not sure how, because of attendance requirements. Wow. You are not here. Very good. That's really smart of you. But thanks for answering, so I know the total number. Okay, so 24 people are here active. Okay, thanks. So out of 24 people, only 4 or 5 are talking. What about the rest of you? Right, so in that case, I mean, I don't think anybody else has thought about it. You need some more domain specific knowledge, yeah? Some knowledge of number theory to get this answer. So now Dhruv can explain.
Yeah, so basically I used this result. So it's called Lagrange's four square theorem. So every natural number can be written as a sum of four squares, four perfect squares. They can repeat among themselves and one of them can be zero also. So if you have that, then the statement is there exist A, B, C, D such that x equal to a square plus b square plus c square plus d square plus y. And now you will see that this expression a square plus b square plus c square plus d square cannot be ever be negative. So this is what we want.
Yeah.
Modulo the theorem.
Good. Thank you. So what happened in the case of real numbers, that difference between like any non-negative real number is a square, whereas every non-negative integer is not a square. So you try, okay, 2 squares, 3 squares, 4 squares, 5 squares, but yeah, you don't have to go to 5 squares, sum of 5 squares. Yeah, you can always get this up to 4 squares, sum of 4 squares. Yeah, that is enough. So this is Lagrange's 4 square theorem. And this, like, once you know such a formula for real numbers, yeah, so then it is natural to ask this question in integers, and it has a name. Yeah, this particular formula has a name. It's called Lagrange's 4 square theorem. Yes. So yes.
Sorry, I just wanted to confirm this thing. Is it possible to find? Is it possible to write a formula satisfying this condition if and only if a greater than or equal to b in this given language, without referring to Lagrange's four square formula?
No. I mean, you are talking about a particular structure, so you have to use some properties of that structure.
But within this structure,
without using Lagrange's 4 square theorem, I don't know. I mean, the only solution I know of is that.
We can go to power force. There is some number 19, I think. Some number is there.
Okay, fine.
And
but
I
yeah,
think
isn't it a derivative of this somehow?
Derivative of, yeah, I mean it is, but yeah,
it
not
should
specific.
use Lagrange's 4 square theorem somewhere.
Okay, yeah.
Okay, sir.
Yeah. So there is a question from YouTube Live that can consistency of PA be written as a first order sentence in PA? Yeah, is that not what SMS did? I mean, I was not paying full attention, but he should have written this statement. Yeah, so you can write the statement that it is not consistent. I mean, it is consistent. PA is consistent itself. There is a Gödel number which encodes that consistency of PA. Anyway, yes, the answer is yes, you can do that. Yeah, consistency of PA can be written as a first order sentence in PA. And that is one such sentence, yeah, which can neither be proved nor be disproved. Okay. Yes, third one is an interesting application. Suppose a theory T in language L has arbitrarily, yes.
Before we move on, the last, like there was an alternative thing given for 2 just now. I did not get that.
Alternative thing for?
For the second one, about some square, something like that. Can you repeat that?
Alternative thing means?
I mean, just the second thing, something else. Someone else gave a solution for this, which you said this is also related to Lagrange.
So that yeah. So Dhruv was again talking about fourth power, sum of fourth powers, which are again going to be non-negative.
Okay.
Yeah. So he said the bound is 19. I'm not sure about that. He has read about it.
No, I'm not sure either. It is somewhere close to that.
Okay. Fine. So, I mean, what we know about it, that all squares are positive, non-negative, all fourth powers are non-negative, sixth powers are non-negative, and we are just trying to take their sums. Okay. Yeah. Third one is an interesting problem, that if your theory has arbitrarily large finite models, then show that it has an infinite model. Okay, so what is the idea? That use the sentence that you constructed above, that it has a model with at least n elements, and then use compactness.
So gamma is the collection of all such sentences.
Gamma is the collection of, so let me call this sentence phi n. Yeah. There is a model with at least n elements. Let me call that sentence phi n. Then I take the union of T with phi n for each n. Now this entire set is finitely satisfiable. Yeah, because T has, so out of these phi n's, only finitely many of them will be used at a time. And such models of T do exist because there are arbitrarily large finite models. And using that, we can use compactness. And using compactness, what do we get? That all the phi n's are satisfied simultaneously, which means there is a model which has at least n elements for each n. Done. Yeah, which means it has an infinite model. And this is a special case of the upward Löwenheim-Skolem theorem. Why I'm calling it a special case? Because you can also show that if your theory has a countably infinite model, then it has uncountable models. If it has models of cardinality kappa, then it has models of cardinality kappa plus, and so on. So all those things are included in the statement of upward Löwenheim-Skolem theorem. But I just gave you the special case that if it has arbitrarily large finite models, then it has an infinite model.
So, sir, this theorem says that if there is a countable model and model for every like finite case,
yeah,
then there are models of any cardinality if you just recurse.
Yes, I mean you don't even need if you have a countably infinite model, then you don't need that there exist arbitrarily large finite models.
Why?
So upward guarantees that everything beyond that cardinality, if it is infinite.
No, you said the hypothesis is that for every cardinality smaller, there is a model, then there is a...
No. So maybe there are some theories which do not have any finite models. For example, algebraically closed fields. Yeah, algebraically closed fields of characteristic 0 is a complete theory. And that has a countable model, namely the algebraic numbers. And using this theorem, you can guarantee existence of complex numbers.
And then there will be
there will be a model. There will be a model in the cardinality 2 to the c. 2 to the 2 to the c. Yeah, there will be arbitrarily large models of this theory.
So, what sort of techniques does the proof of this theorem use?
Compactness. You have to include lots and lots of constant symbols in your structure and use compactness. Proof is not hard.
Talks about finite.
Yes, so you show that every finite subcollection of that theory union certain sentences has a model, yeah, which is guaranteed by what you already have, and then you say that there exists. Yeah, it is not hard. Yeah, you just need to know what cardinals are, and you can do that. You add appropriately many constant symbols, and then perhaps you can add the sentences which we had like that, some atomic sentences, that C1 is not equal to C2. Yeah, so C is not equal to C prime. You had to add all these sentences for all the new symbols. Yeah. Suppose you are interested in cardinality C. Yeah, I mean, then you add constant symbol C1, C2, like indexed by this cardinality of real numbers. And then you add this atomic sentences which say that any two constants are different. I mean, that is not a single sentence. You add one sentence for saying any pair is distinct. And that is finitely satisfiable, so it has arbitrarily large models. That is the power of compactness. Yeah, if you know, and there is a downward Löwenheim-Skolem theorem. So for example, you know what complex numbers are. Complex numbers are algebraically closed. But downward Leeuwenhoek's-Coulomb theorem will tell you that there exists a countable model of this theory, like in the lower cardinality, which means algebraic numbers exist. They are a countably infinite algebraically closed field.
What is the hypothesis for downward theorem?
No, the hypothesis is always the same, that a
But
theory
then you said
has.
there are some theories which have countable model but no finite model.
Yeah. So the statement reads like this: suppose a theory T in any language L has a model in cardinality kappa, where kappa is infinite. Then there exists model of this same theory in every lower infinite cardinal.
Infinite cardinal, okay.
Yes. Every lower infinite cardinal, not arbitrarily. Yeah.
So basically, if there is a model which is infinite,
yeah,
then for every infinite cardinal there is a model. Can we say for using downward and upward combination?
Yes. That's true.
Okay.
Yeah, that's true. Yes. So now here are some simple questions. Yeah, use Walsh's theorem to show that a sentence theta is true in R if and only if it is true in star R. So I will directly take you to the solution of that. Yeah. So look at this last, the solution of the fourth problem. Yeah, Walsh's theorem, star R has theta, theta is true in star R if and only if this happens. But because all the component structures are just copies of R and empty set is not in U. So this happens if and only if R is a model of theta. Yeah, so this is if and only if this is if and only if this, and we are done. So I will upload this tutorial sheet as well. Yeah. Any questions about this? Okay. I mean, I still have a couple of things to do. So using properties of ultrafilters, show that each non-zero element in star R has a multiplicative inverse. This I said yesterday, yeah, how to get the multiplicative inverse. Let me show you the proof in writing. So let An be a non-zero element, like its equivalence class is non-zero. Then what will happen, that the collection of those indices where An is equal to 0 is not in U. Yeah, it is a small set of indices. Then obtain a sequence Bn which is equivalent to An and which does not contain anything 0. You just change all the zeros to something different. They will still be equivalent. And then 1 over Bn is the multiplicative inverse of An. Yeah, so you can make some changes in the sequence, like if it contains some zeros on a small set of indices, then you can replace them by ones and just take the inverse of each of the entry, and that gives you an inverse for the original one. So we have seen these things, but I wanted to put these things in writing so that you can have a look at it later on. Okay, one more application, like this is a standard application of compactness that you can show. Yeah, you can show that hyperreals exist using compactness. Yeah, we directly constructed something, like we used existence of ultrafilters, but you can actually show that. What is the idea? Yeah, let us take the language of rings. And yeah, you can either define less equal or add it in the language, doesn't matter. And you expand this language by adding a constant symbol epsilon. And you add these sentences, whatever properties you want, that epsilon is greater than 0 and n times epsilon is less than 1 for all n in n. And you add this to the theory of real numbers. Yeah, and show that there is a model of TR containing infinitesimals. The idea is again very similar, that this collection is finitely satisfiable and therefore it is satisfiable. So there will be infinitesimals in some model. So here is a proof of that. Yeah, so I have just written down everything formally. So what is the interpretation of epsilon for a finite subset of this? It is 1 over nk plus 1, where nk is the largest, such that theta nk is in the finite subset of T of this, yeah. And then use compactness. So compactness is extremely powerful tool. You can construct proper something like Erdős-Rényi random graphs using compactness. Yeah, random graphs means like with some probability p, you decide. So you are given a countably infinite vertex set, and with some probability p, you decide whether you want to put an edge between this pair or not. And all the properties of such random graphs can be captured using compactness.
How so?
I mean, that is the theory, yeah. So what are the properties of random graphs? That it contains arbitrarily large cliques, which means complete graphs, arbitrarily large finite complete graphs, and also arbitrarily large empty graphs as induced subgraphs. Then you can also require that, I mean, you can also demonstrate the existence of any subgraph. Yeah, any finite graph will appear as a subgraph of that, induced subgraph of that.
But it will appear randomly, right? How are you putting it in this setting?
By using yeah, let me think about it. I mean, just one more thing I want to say.
Okay.
Maybe I'm making some mistake. So I think I wanted to talk about countable categoricity. And that is what I have expressed in the 7th problem. That the theory of dense linear orders without endpoints has one countable model, countably infinite model, that is rationals. So in fact, any two countably infinite models of this theory are isomorphic. So this is called countable categoricity. And a similar result is true for Erdős-Rényi random graph as well. That there exists a unique countably infinite random graph. Yeah, and here is the, yeah, so this I'm definitely leaving, but this is like beginning of model theory. This is called the back and forth method, and the conclusion is stated as countable categoricity of the theory of dense linear orders without endpoints. So you actually try to set up a bijection between points of those two distinct dense linear orders. A1 matches to something, then this matches to something, and you have to use all the axioms that between any 2 points, you can find a third one. Below everything, you can find a new one. Above everything, you can find a new one. And using those properties, you can actually set up a bijection using induction. That is called the back and forth method. And using that, you can see that any two such models are isomorphic. Yeah. If Sujata is here, and yeah, right now I don't know how to, how compactness is coming into picture for this finite random graphs, but sorry, countably infinite random graphs. Sujata, are you there? Okay, perhaps not. Yeah, I mean, if you are interested, I can.
I am here, but I didn't I didn't understand your question. I was doing something else.
Okay. So I think I said something wrong here, that compactness is useful in showing existence of Erdős-Rényi random graphs. Perhaps I shouldn't have said that. I just wanted to say the countable categoricity.
Yeah, maybe.
Okay, yeah.
Yeah.
Yeah, any questions about this? Like, I had to rush through this last part because of time constraints. The host will stop me anyway. Any questions from the participants?
Sir, what was the conclusion of the discussion as well? I didn't understand. Countable categoricity.
Countable, yeah. So you, for any given cardinal, you can ask for categoricity, which means existence of a unique model up to isomorphism. So, I mean, because you asked about this, there is one very interesting theorem known as Morley's categoricity theorem. It states that if your theory has categoricity in some uncountable cardinal, then it is categorical in all uncountable cardinals. Like algebraically closed fields with characteristic 0. Yeah, that is one such example. Like complex numbers is the unique model in that cardinality. And therefore, in every cardinality, there exists a unique model. This is a very powerful result.
Sir, is there some example? What is an example of such a thing?
Of what? Example
of something having this uncountable categoricity?
Yeah, I mean algebraically closed fields with characteristic 0 or characteristic P. Any P will work.
Okay.
This needs lot of machinery to prove Morley categoricity theorem. And if you take a course on model theory, that is usually where you would try to go. Although, yeah, for a semester long course, that is a bit too much. Yeah.
There is a nice connection between categoricity and complete theories as well.
Okay.
Meaning, you can. I'm talking about this Washford theorem.
Okay, okay. Wash and what?
Yeah,
I know Tasky what test, but yeah, I haven't heard of this Washford.
Okay. So categoricity is complete then.
Categoricity in any cardinality, uncountable cardinality implies completeness.
Something like I don't remember the exact statement. It's a relationship between categoricity and being a complete theory, and so that's kind of the thing.
Okay, so thanks, Sujata. There is one last question from YouTube Live. Are there two non-isomorphic uncountable models of the last exercise? Yes. Yes, for DLOs there are. Yeah. You can actually take real numbers.
Sorry. I think you can put two real number lines together.
Yes. Yeah. Real numbers and real numbers, reals and rationals, one copy and then another copy. Yeah. So those things will do. So there are.
Sorry, Amit. Since I got involved in this discussion, may I state it now?
Yeah. Sure.
Yeah, it's just for the students. So it's basically what I was talking about, this Washford test. It says that if a theory is Alephnull categorical, then the theory is complete.
Okay. Yeah. That I mean. Yeah.
If the theory is kappa categorical for some infinite cardinal kappa, then the theory is complete as well. That's what I meant.
Right. Yeah, this is Alephnull categoricity. And yeah, I mean, that was another missing link. Yeah. People asked me earlier that how do you conclude that Q is a model? Like this theory is complete because Q is a model of this and it is categorical. Alephnull categorical, therefore Q is the only model and the theory is complete. Yeah, any questions? The number of participants is going down because I'm talking about something hi-fi. Yeah, Dhruv.
Sir, when you say two models are same for a language, for an arbitrary language, what is the notion of the isomorphism?
What do you mean by same? Same is isomorphism, right?
So you said that there is only one model for a given cardinal. So suppose I have two different labelings. So
up to isomorphism. Up to isomorphism.
What is the isomorphism in this setting?
In this setting?
Yeah, in
DLOs.
Huh?
Yeah, that in order to construct that isomorphism, you have to go through this back and forth.
No, sir. Not just this less than equal to, like for a general language.
For countable categoricity, I think you always use back and forth method.
Sir, I'm asking about the definition for a general language. When are two models isomorphic?
If there exists a bijection between their universes which preserves and reflects truth of every symbol in the language.
Yep.
Yeah.
Are there any other questions from the participants? Okay, probably not. As you all might be aware that this was the last lecture in the series by Dr. Amita Kuber. So thank you, sir, for the wonderful series of lectures. I'm sure that the student gained a lot from this. So thank you so much.
Thank you. And thanks to all the participants who survived until this point. Yeah.
Thanks, Amit. Yes, I mean, yeah.
Okay, so I'll turn on.
With any questions, yeah, please feel free to contact me anytime. Yeah, I always respond to emails. Yeah, thank you, people writing in the chat. Yeah. Oh, Sujata, did I make a mistake?
No,
Reflection.
No,
reflection also.
No. I just said that. No, I just wanted to mention it
in the chat, right?
Yeah.
Yeah, thank you all. You have been a very good set of students, and yeah, usually it's rare to see so many people attending logic lectures. I teach a compulsory course, but yeah, those students have to be there because they have no other option. It's a compulsory course. But yeah, all the participants are here with their own choice. So thanks a lot. And keep studying logic. Yeah, that is our main motivation for running this school.
Yeah, maybe we can say something more at the, of course, to the participants who remain at the end of the school, till the end of the school.
Till the next school, yeah, definitely.
And also till the end of this school, so that what are the things that are going to happen in the vicinity. There are loads of events that are going to happen in the vicinity, even courses as well as, so we can mention all of them if you are interested.
Yeah. There will be a course on modal logic sometimes in January by Sujata. That will happen online.
Yes.
Under the umbrella of Logic webinar at IIT Kanpur. Yeah, I'm just plugging that in. If few people are still around.
Yeah, thanks for the advertisement.
Okay, thank you, everyone. We'll meet tomorrow at 10 a.m.
And everybody can email me. Yeah, so I'm getting private messages. Yeah, you can definitely email me anytime. Yeah, I will be happy to respond. And tomorrow, so please, those who are going to present tomorrow, I will put up some timetable by tonight. Yeah, for that. There are 7 presentations as far as I know. So I'll put up a timetable for tomorrow afternoon session. Bye.